All right, let's dive right into this explainer and immediately break a massive illusion. We really need to shatter the idea that programming a quantum computer is just, writing a faster version of an ordinary classical program. It's not a magic CPU running your standard while loops at lightning speed. Today, we're zooming out to look at the big picture of what quantum programming actually is in practice. We're treating it not as some mystical sci-fi concept, but as a rigorous, practical engineering stack.
Here is our roadmap for the rest of the explainer. We'll contrast the classical illusion with quantum reality, explore the quantum experiment model, unpack the hybrid pull stack, dig into probabilistic circuit execution, see why hardware and compilers dictate absolutely everything, and finally preview our entire series arc.
Section 1. The classical illusion versus the reality.
To truly grasp the subatomic computational space, we have to completely throw out the classical deterministic paradigm we're all so used to. This is the fundamental paradigm shift. A quantum computer is an accelerator that manipulates quantum states. You aren't writing standalone applications, you're writing highly specialized statistical kernel executions. You're initializing qubits, applying unitary gates, and measuring selected qubits to return classical samples.
Moving right along to Section 2, the quantum experiment model.
So, a quantum program is much better understood as a highly specialized physics experiment. Think of it this way. The core quantum logic functions as a really narrow, targeted subroutine, a quantum kernel. The quantum program is literally just this kernel. The entire rest of your pipeline, from formulating the domain problem to preparing the data and orchestrating the jobs, that all remains entirely classical.
And every single practical quantum program follows this exact life cycle. You choose an initial state, then you design transformations so the right answers interfere constructively, building up probability before you measure in the appropriate basis. Finally, you rely on classical post-processing to infer the actual result. You are quite literally orchestrating a state preparation and measurement experiment.
Because of the sheer complexity of orchestrating all that, we land at Section 3, the hybrid full stack.
Current gate model quantum processors are noisy, they're heavily hardware constrained, and frankly, they cannot run deep applications reliably on their own. So there's a strict division of labor here. Classical software handles all the heavy lifting, formulating the problem, optimizing parameters, scheduling jobs. Meanwhile, the quantum processing unit acts strictly as an accelerator, handling only the specialized unitary evolution, the sampling, and the analog evolution.
This division creates an iterative feedback loop, which is really the heartbeat of algorithms like the variational quantum eigensolver. It's essentially this high-speed negotiation. The classical optimizer proposes circuit parameters, the QPU runs the noisy trial and estimates values, and then the optimizer updates those parameters. It's a tightly coupled, constant dance between conventional cloud workflows and the quantum hardware itself.
Let's drill into exactly why that feedback loop is so necessary in Section 4, probabilistic circuit execution.
This is where your conventional debugging instincts are going to completely break down. Unlike a deterministic classical function, you cannot freely inspect a quantum state. Because of the bizarre rules of quantum mechanics, specifically things like the no-cloning theorem, there are absolutely no print statements here, none. You can't just pause your code, check a variable, and resume. The act of measurement probabilistically collapses the state entirely, instantly destroying the superposition you worked so hard to build.
Therefore, your circuit must be executed repeatedly. We're talking thousands of times. SDKs call these iterations shots. You use these shots to build up a statistically valid distribution. You aren't just checking if a Boolean flipped to true. You're applying rigorous statistical error analysis to a massive set of runs just to find an estimator with reliable confidence intervals.
Which brings us down to earth for Section 5, Hardware and Compilers Rule in 2026.
In the quantum realm, hardware is not some abstract concept. It is your master. Physical constraints dominate absolutely everything. These aggressive constraints dictate whether a mathematically perfectly correct source program will return any usable evidence at all. You have to be hyper-aware of your circuit depth because decoherence will destroy a poorly mapped circuit over time. You also have to battle calibration drift, meaning a circuit that executed perfectly yesterday might map to much noisier qubits today.
Superficial code elegance? It really doesn't matter here. What actually determines your exposure to errors is the post-transpilation execution, the circuit that has been aggressively rewritten to match the specific device topology. If your two target qubits aren't physically connected on the hardware chip, well, the compiler has to intervene, inserting routing and swap operations. That extra overhead can completely dominate and ruin beautifully written source code. If you take away just one concept today, let it be this. In quantum computing, the compiler is literally part of the algorithm, especially when dealing with intermediate representations. The compiler pipeline performs the decomposition, the routing, the scheduling, and the measurement optimization. Simply put, if you don't understand what the compiler is doing to your circuit, you don't actually understand what your program is doing.
Now that we've shattered that classical illusion, let's zoom out to Section 6, the series arc and your learning journey. We are treating this as a rigorous engineering discipline spanning 19 more segments. We're going to systematically build your knowledge stack. We'll start with math foundations and circuits, then move into intermediate representations and major SDK ecosystems like Qiskit, PennyLane, and Q#. After that, we'll tackle the really hard stuff: hardware-aware compilation, error mitigation, and eventually fault-tolerant logical qubits. It is a massive, comprehensive workforce pathway.
The shift from deterministic classical coding to probabilistic, hardware-aware quantum experimentation requires an entirely new mindset. The best quantum programmers of the near future are going to be hybrid engineers, part algorithm designer, part compiler wizard, and part statistician. Look at the stack we've mapped out today and ask yourself honestly, are you truly ready to completely rethink computation? Let's jump right into segment 2 of our explainer. We're breaking down the absolute foundational mathematical models needed to understand quantum programs. We're starting right from the bare metal to show exactly how a quantum computer stores and processes information long before we ever reach the application layer.
Here's how we're going to build this up. First, we'll tackle qubits and complex amplitudes, then move into tensor products and scaling. After that, we'll look at why measurement is an actual operation, how changing the measurement basis works, and finally, why quantum programs are really just statistical experiments.
Section 1. Qubits and complex amplitudes.
What's truly fascinating here is how this completely redefines information storage at the lowest possible level. Think about the classical bit. It's strictly deterministic. It's always a 0, or it's a 1. But a qubit, it isn't just a switch. It's a normalized vector. It's defined by a linear combination, a superposition, written out as alpha 0 plus beta 1.
Let's aggressively label these components so we know exactly what we're dealing with. Alpha and beta aren't just generic variables. They are complex numbers called amplitudes. And the math dictates that their squared magnitudes, the absolute value of alpha squared plus the absolute value of beta squared, must equal exactly 1. Those squared magnitudes strictly determine the probability of measuring a 0 or a 1. To make this a bit more intuitive, you can visualize this single qubit state as a point on the surface of a three-dimensional block sphere. It gives us a highly intuitive geometry for a single unit of quantum information. Any valid pure quantum state can be mapped somewhere on this continuous surface, which is obviously a massive departure from a simple classical toggle switch.
Now, here is a crucial point, and honestly, a very common beginner anti-pattern: confusing amplitude with probability. Notice the distinct differences here. Amplitudes are complex numbers that have a phase. They're the active engines that drive the computation by interfering with one another. Probabilities, on the other hand, are real numbers, calculated via that squared magnitude, and they only emerge after the math collapses during a measurement.
Moving right along to Section 2, tensor products and scaling.
Let's see how this builds when we combine multiple qubits into a single system. Multi-qubit systems are represented mathematically by tensor products, creating a state space that scales exponentially at 2 to the power of n complex amplitudes. So 1 qubit is 2 amplitudes. 10 qubits jump to over 1,000. But remarkably, by the time you reach just 50 qubits, the system's state vector requires 1.12 quadrillion complex amplitudes to describe it.
And this brilliantly illustrates a core reality of quantum engineering. This exponential scaling is incredibly powerful, but it isn't some magic parallel processing. You have to actively program the algorithm to create constructive interference. You're trying to amplify the correct answer and cancel out the wrong ones, so that when you finally look at the system, the useful outcome is actually the one most likely to appear.
Which brings us to Section 3. Measurement is an operation.
To really grasp this, we have to shatter a classic illusion from classical computing. In standard software, you can just throw in a print statement to look at a variable mid-execution, right? Well, you absolutely cannot do that in a quantum program.
Measurement isn't a passive read. It's an aggressive, irreversible physical operation. It physically projects and collapses the quantum state entirely.
Because of that collapse, every quantum program fundamentally acts as a state preparation and measurement experiment following 3 distinct steps. Step 1 is state preparation, setting up your initial high-dimensional state. Step 2 is constructive interference, applying unitary transformations to manipulate those complex amplitudes. And Step 3 is measurement, physically projecting that massive quantum state down into a single classical result.
All right, Section 4, changing the measurement basis. Measurement isn't just pointing a camera and taking a picture. You actually have to tell the program how to look. The measurement basis is the specific observable property, like the x, y, or z axis of that blotch sphere we talked about earlier, onto which the quantum state is projected. Because measuring projects the state into an eigenstate of your chosen observable, the basis you actively choose dictates the specific kind of classical information you reveal. Here are the standard basis rotations you'll actually use in code. If you measure directly, you get standard computational Z basis information. But if you want to observe a poly X property, you have to actively apply a Hadamard gate, the H gate, just before measuring. To observe a poly Y, you apply an S dagger and a Hadamard gate, and then measure. You literally have to physically rotate the qubit in software to align with your measurement tool.
Finally, Section 5, programs as statistical experiments.
We really need to understand the concept of a shot. A shot is a single execution of a quantum circuit followed by a measurement. Because measurement violently collapses the state, one shot returns exactly one sampled classical outcome. You get a single bit string. You do not get to see the underlying complex distribution of amplitudes. To actually see the probabilities driven by those complex amplitudes, you have to run the circuit over and over again. You execute thousands of shots, accumulating the individual classical bit strings into a statistical histogram. The varying heights of that histogram represent the accumulated frequencies, and that is exactly how we estimate the underlying expectation values.
Which leads us to the ultimate engineering reality. Quantum programs are, fundamentally, statistical experiments. A developer doesn't just write a function and get a definitive return value. They have to constantly reason about probability distributions, calculate observable expectation values, manage tight shot budgets because running the hardware is expensive, and rigorously account for confidence intervals and statistical variance.
And that leaves us with a massive, fascinating engineering challenge to ponder. If you can't freely inspect the state of your system, if merely observing the data destroys the entire calculation, how on earth do you test and debug your software?
Let's jump right into the core logic layer of quantum programming. If we're going to actually write code for these machines, we have to completely stop thinking of quantum computing as some sort of magic or just a faster version of an ordinary program. It's an engineering stack, and at its very foundation, it is an exercise in managing math, software logic, and incredibly strict hardware constraints. Every quantum program you write usually expresses a specialized computational kernel as a quantum circuit, which is essentially just a sequence of gates, measurements, and resets.
So here is what we are covering in this explainer today. 1. Unitary transformations and single qubits. 2. 2-qubit gates and entanglement. 3. The Bell state sanity test. 4. The reversibility programming constraint. 5. Gate families and fault tolerance. And finally, 6. Executing circuits on real hardware.
Section 1, unitary transformations and single qubits.
So, at the foundational atomic level of computation, what exactly is a quantum gate? Well, it's definitely not a physical switch like a classical transistor. It's actually a linear, norm-preserving, reversible mathematical matrix operation. We call this a unitary transformation. When you apply a gate, all you're really doing is multiplying a state vector by a unitary matrix to manipulate the complex amplitudes and phases of your qubits before you measure them. That is the actual engine of quantum computation. Think of this as the basic vocabulary of quantum circuitry. You've got your poly gates, X, Y, and Z, which execute pi rotations around the axes of the Bloch sphere. Then you have your phase and superposition gates like the Hadamard or H gate, which creates superposition, as well as the S and T gates, which shift the phase. And then you've got continuous parametrized rotations like Rx, Ry, and Rz, which let you rotate by arbitrary angles. You really need to aggressively burn these labels into your mind because they are the absolute bedrock of writing quantum source code.
Moving right along to Section 2, 2-qubit gates and entanglement.
All right, so what happens when we want multiple qubits to actually interact and correlate?
2-qubit gates become the physical building blocks of entanglement. But here is where the messy reality of hardware starts creeping into our abstract math. The universal standard gates you write in your code are typically the C0 or controlled NOT and the CZ or controlled Z. But listen to this. Different hardware modalities natively execute entirely different entangling gates. Superconducting processors, for instance, might natively use ISWAP-like operations. Trapped ion systems, on the other hand, often expose Molmer-Sorensen-style gates. So your compiler literally has to translate your standard C0 into whatever language the physical hardware actually speaks. And this brings us to a crucial point. Entanglement is a strict mathematical property. It's not science fiction. Entanglement simply occurs when a multi-qubit state cannot be factored into separate, independent single-qubit descriptions. As quantum software engineers, we actively avoid hype terms like spooky action. For us, entanglement just means that our outcomes are mathematically correlated in a specific way that independent classical variables simply cannot represent efficiently.
Section 3. The Bell State Sanity Test.
Think of this as the hello world of quantum programming. If you were to boot up a framework like Qiskit or PennyLane right now, this is the exact procedural sequence you would write to test your logic. Step 1. Initialize 2 qubits in the 0-0 state. Step 2. Apply a Hadamard gate to the first qubit, putting it into a superposition of 0 and 1. And Step 3. Apply a C0 gate, using that first qubit as the control and the second as the target.
This brilliantly illustrates what happens when abstract math meets the actual machine. When you measure this circuit, the entangled state collapses. Now, on ideal, mathematically perfect hardware, your outcomes concentrate perfectly on 0-0 and 1-1. They aren't two independent random bits, they're completely locked together. But if you run this exact same code on real, noisy hardware, suddenly unexpected 0-1 and 1-0 outcomes will appear. So this simple pattern becomes your very first vital sanity test for hardware noise.
Section 4. The Reversibility Programming Constraint.
Let's compare these two paradigms, because making this jump requires a complete rewiring of how you think about writing software. Classical logic is inherently irreversible. When you use an AND or an OR gate, you literally destroy information. You can't perfectly reverse the computation to find out what the inputs were. But quantum logic? It's reversible. Remember earlier when we said our gates are unitary matrices? Because they are unitary, most operations before measurement must be completely reversible. So if you want to run classical logic, like a database search, you actually have to structurally embed it into reversible computations.
So, how do we pull that off? We use ancillary or helper qubits. But wait, that introduces a massive problem of its own, garbage entanglement. If you leave temporary values just sitting around on these ancillary qubits, they remain entangled with your output, and they will completely destroy the interference patterns you need to get the right answer. So we rely on a design pattern called uncomputation. You compute, you use the result, and then you strictly apply inverse operations to uncompute those temporary values, clearing them out entirely.
And this isn't just academic theory. This reversibility constraint literally dictates the code architecture of major algorithmic families. When you're writing oracles for Grover search, setting up reversible arithmetic, designing phase kickback routines, mapping modular arithmetic for Shor's algorithm, or building quantum phase estimation, you absolutely must strictly manage this reversibility and uncomputation. Forgetting to uncompute is one of the most common, fatal bugs in quantum programming. It's basically the quantum equivalent of a catastrophic memory leak.
Section 5. Gate Families and Fault Tolerance.
Which leads us to a really interesting question. Why do we even care which specific gates we use if they are all just unitary transformations? Math is just math, right? Well, computationally and physically, some gates are vastly more expensive to run than others.
This is where we have to divide our gates into two vital families. First, you have your Clifford gates. According to the Gottesman-Kill theorem, circuits made entirely of Clifford gates like X, Y, Z, Hadamard, and C0 can actually be simulated efficiently on a classical computer in polynomial time. They are structurally vital for quantum error correction, but on their own, they will never give you a quantum advantage. For universal computation, we literally must inject non-Clifford gates, like the T-gate.
But here is the harsh engineering reality for future fault-tolerant settings. Non-Clifford resources, like those T-gates, become overwhelmingly expensive. They can sometimes consume over 90% of your physical qubit budget because they require this incredibly complex, resource-heavy process called state distillation or magic state distillation.
When you're designing algorithms for error-corrected machines, your t-count and your t-depth become your absolute most critical cost metrics.
Section 6. Executing circuits on real hardware.
Let's bring this all together. The code you write on your screen is just the clean source circuit, but a mathematically correct program is literally only the starting point. Before it ever actually hits the hardware, the compiler deeply intervenes to create the executable reality.
Because quantum programming is ultimately an exercise in resource constraints, the compiler pipeline handles all the heavy lifting here. First, native gate composition translates your abstract gates into the hardware-specific language. Then comes routing and swap insertion. You see, if your hardware doesn't allow two specific qubits to talk directly to each other, the compiler has to insert swap gates to physically move the information, which drastically increases the depth of your circuit. Then it has to handle scheduling for timing, measurement basis rotations, and finally, classical post-processing and error mitigation.
And keep in mind, this pipeline changes completely depending on the physical hardware you target. If you are compiling for superconducting qubits, you're dealing with fixed, lattice-like connectivity. That requires heavy routing and lots of swap insertion, which balloons your circuit depth and heavily exposes you to decoherence noise. But if you compile that exact same code for trapped ion qubits, you have all-to-all connectivity. That practically eliminates your swap overhead, but trapped ions have slower gates, which introduces completely different timing and scheduling trade-offs for the compiler to manage. Which leaves us with a final, vital question for this explainer. As you step away from pure theory and begin building your own quantum software stack, you have to ask yourself, are you still just designing for perfect abstract math, or are you actually architecting for the physical, messy constraints of the machine? Because in quantum programming, the compiler is not just a back-office tool, it's a fundamental part of the algorithm itself. Keep that front of mind as we continue exploring the next layers of the stack.
Let's just dive right into this explainer by immediately shattering one of the biggest myths in quantum computing, the idea that there's just one single, universal quantum programming syntax out there. If you're coming into this hoping to find the quantum equivalent of just writing a script in C++ or Python, well, you're not going to find it. Instead, we're looking at a really rigorous, diverse family of programming models. Today, we're setting the stage for a comprehensive tour of the quantum software landscape. We're going to map out exactly how developers are translating all this complex math into physical reality on actual quantum processors.
Here is our roadmap. We'll be covering the quantum programming family, the mainstream gate model, hybrid and differentiable models, lower level and logical control, alternative paradigms beyond circuits, and finally, the engineering stack reality.
Section 1. The Quantum Programming Family, a taxonomy of models.
The absolute most crucial thing to understand here is that quantum programming is a family of completely distinct paradigms. You aren't just picking a syntax preference, like choosing between Python or Java. The model you choose completely dictates your entire engineering stack. It dictates your source language, how your compiler behaves, how you validate your results, and even your ultimate metrics for success. What it actually means for two programs to be equivalent changes entirely depending on whether you're working with discrete gates, energy models, or physical microwave pulses.
Okay, Section 2, Mainstream Gate Model, Circuit Abstractions.
Let's look at the absolute most common abstraction used in public universal quantum programming today. This is the gate model circuit. In this setup, horizontal wires represent your individual qubits, and the operations, the quantum gates, are ordered sequentially, moving left to right through time. It's a pretty straightforward flow. You initialize the qubits, apply these unitary gate transformations to build up interference and entanglement, and finally, you measure the qubits at the end to pull out your classical bit strings. To really ground this in the real world, you need to know that this gate model abstraction totally dominates the current ecosystem. We're talking about Qiskit, which is the massive industry standard centered around IBM hardware. Then you've got Cirq from Google, which is fantastic for granular gate scheduling. There's Q# from Microsoft for structured algorithmic development. We also have Amazon Bracket for cloud-agnostic circuit tasks that span across multiple hardware vendors, CUDA-Q for bridging quantum workflows with high-performance computing, and absolutely essential compiler tools like TKAT from Quantinuum. All of these massive tools, they all speak the language of the gate model circuit abstraction.
Section 3. Hybrid and differentiable models. QPU as an accelerator.
Moving into the pragmatic present, let's explore the hybrid quantum classical loop. Look, because current quantum hardware is noisy, we just can't run exceptionally deep, flawless circuits right now. Developers treat the quantum processing unit, or QPU, as a specialized accelerator subroutine. This workflow breaks down super cleanly into 3 steps. First, a standard classical computer chooses the initial parameters and manages the batching.
Second, the QPU runs the parameterized circuit and estimates samples or expectation values. And third, the classical optimizer validates that output, calculates how to improve it, and updates the parameters for the very next circuit run. This exact loop is the beating heart of near-term heuristics, like the variational quantum eigensolver or VQE used in chemistry, and QAOA used for combinatorial optimization.
Taking that hybrid concept a step further, we arrive at differentiable quantum programming. This is a model where quantum circuits behave exactly like trainable differentiable functions sitting inside a much larger classical computational graph. PennyLane is the major software framework built entirely around this paradigm. By treating the quantum circuit as a differentiable node, you can actually use classical machine learning techniques, think automatic differentiation and gradient descent, to literally train the quantum circuit. This is what unlocks quantum machine learning, variational chemistry, and gradient-based optimization workflows across all sorts of different backends.
That brings us to Section 4, Lower Level and Logical Control, Hardware to Logic.
Now, let's dive right down into the bare metal, and then immediately look way up at the scalable future. This comparison perfectly illustrates the huge difference between programming physical hardware today versus error-corrected structures tomorrow. On one hand, you have pulse-level programming. This strips away the circuit abstraction entirely. It exposes the raw microwave schedules, waveforms, readout instructions, and custom gates. It is incredibly sensitive to daily hardware calibration, and researchers use it to squeeze literally every ounce of performance out of a noisy chip. On the flip side, we have fault-tolerant logical programming. In the future, large-scale programs won't target bare physical qubits at all. They're going to target logical qubits protected by error-correcting codes. The programming focus shifts entirely to scheduling stabilizer cycles, managing decoders, running magic state distillation factories, and executing logical gates.
Bridging the gap toward that fault-tolerant future are dynamic circuits. Now, a dynamic circuit doesn't just run blindly and measure at the very end. Instead, it actually combines mid-circuit measurements, qubit resets, conditional operations, and real-time classical control flow right inside the execution window. So if a mid-circuit measurement returns a 1, a classical controller instantly triggers a specific conditional quantum operation on another qubit. This real-time feed-forward capability is absolutely essential for things like teleportation, active reset, qubit reuse, adaptive algorithms, and most importantly, the error correction routines that will eventually make logical qubits possible.
Now, just a quick point of clarification here to help separate your daily developer workflows from sci-fi novels. You've probably heard the phrase topological quantum computing. It is vital to firmly position this as a brilliant, long-term hardware and fault tolerance architecture. It's all about storing information non-locally by braiding anyons to suppress local noise. However, it is not a mainstream, day-to-day public programming target right now. You just don't log in and write topological code today the way you sit down and write a Qiskit circuit.
Let's move on to Section 5, Beyond the Circuit Abstraction, Alternative Paradigms.
Stepping entirely outside the circuit model, we find architectures that rely on completely different mathematical paradigms. First up, quantum annealing. You don't write gates here at all. You program an energy model, specifically Ising, Kubo, or binary quadratic models. You encode your problem, so the answer lies in the ground state of a final Hamiltonian, and then you just let the system evolve. D-Wave's Ocean SDK is the absolute standard here. Second, analog Hamiltonian simulation. Used heavily with neutral atom hardware like Quera via Amazon Bracket, the program here isn't discrete gates, but time-dependent and space-dependent physical parameters like geometry, detuning, and interaction schedules. Finally, measurement-based quantum computation. Instead of applying gates, you prepare a massive, highly entangled resource state, like a cluster state, and you drive the computation entirely through adaptive local measurements and classical feed-forward.
Finally, Section 6, the engineering stack reality, choosing your model.
And this really brings us to our final thesis. Quantum software is a rigorous engineering stack. The specific programming model you choose dictates absolutely everything downstream. It dictates your source language in SDK, it completely redefines the compiler problem. For a gate model on superconducting chips, your compiler is fighting a routing and layout problem to minimize swap gates. But for a quantum annealer, your compiler is fighting a minor embedding problem to map a logical graph onto physical hardware. It dictates your validation and testing methods, shifting from exact state vector simulation over to statistical assertions, and it determines your ultimate success metrics, whether you're measuring circuit depth and T-count or optimizer evaluations and measurement overhead. The model literally changes everything. So,
As we wrap up this explainer, I want to leave you with a central question to think about for your own workflows. As you look at the domain problem you're actually trying to solve, whether that's drug discovery, logistics routing, or materials science, ask yourself this. Does your specific problem require a coherent gate model circuit, a classical quantum hybrid loop, a physical analog schedule, or a fault-tolerant logical decoder? Answering that question right there is step 1 to mastering quantum programming.
Look, quantum programming often gets a bad rap. It gets shrouded in this aura of mystical sci-fi magic, but today, in this explainer, we're going to tear that veil down completely. We're looking at the actual quantum program lifecycle, taking you from the initial problem formulation all the way to rigorous, reproducible evidence. We're going to treat quantum programming exactly as what it's become today, a brutal, rigorous, iterative engineering stack. One that combines dense mathematics, heavy software layers, massive hardware constraints, and intense statistical analysis. So let's just get right into the mechanics of how this actually works.
Okay, let's dive into this, because the paradigm shift is huge. Classical programming, which we're all super used to, relies entirely on deterministic function calls, right? You put a specific input in, you predictably get a specific output back. But quantum programming, totally different beast. It is fundamentally a state preparation and measurement experiment. You aren't just writing a slightly faster classical program, you are literally designing and running an experimental physics apparatus in code. You initialize a state, you design specific transformations so the right answers interfere constructively, you measure it, and then you heavily rely on classical post-processing just to figure out what happened.
So to understand how this experimental apparatus is built, we're going to follow a 5-step chronological journey today. 1. Formulation. 2. Construction. 3. Compilation. 4. Execution. And 5. Post-processing. This is the exact sequence every modern quantum engineer navigates to get anything even remotely useful out of a QPU. Let's start right at the beginning with stage 1, formulating the quantum problem. This is that critical first translation step where your real-world task, whether that's cryptography, optimization, machine learning, gets translated into a format the hardware can actually digest.
Here's the reality. A quantum device absolutely doesn't care about your business logic. It only understands highly specific mathematical objects. We're talking about a Hamiltonian, an oracle, a cost function, an observable, a unitary, a probability distribution, an Ising model, a Kubo, or an analog control schedule. And honestly, this mathematical translation is almost always way more important than the syntax of whatever SDK you happen to be using. Because think about it. If you formulate an optimization problem into an overly dense Ising model, the hardware routing overhead alone might crush your program before it even executes. The math you lock in right here dictates the exact physical burden you're about to place on the device.
Now, what's really interesting about this next slide is how we shift from that abstract math into actual code. Stage 2, construction and validation.
First up, developers take those mathematical objects and start constructing circuits, parameterized onsets, observables, or annealing autos using standard tools. Qiskit, Circ, PennyLane, Bracket, CUDA-Q. But then comes step 2, and this is crucial. You absolutely must run small instance validation layers before you ever even think about touching the actual hardware. You're spinning up state vector simulators for pure state evolution, noisy simulators to check statistical behavior, maybe tensor network simulators depending on your model. This is your essential first line of defense to check your logic and estimate resources before you burn time on a deeply constrained, highly expensive physical QPU.
And here is exactly why that simulation step is so non-negotiable. Quantum state cannot be freely inspected without measurement, right? And the no-cloning theorem blocks any simple snapshot and copy debugging. In classical code, if something breaks, you just set a breakpoint, stop execution, and inspect your variables. You cannot do that here. Direct observation fundamentally changes the quantum state. It's literally like trying to check if a cake is baked by opening the oven door, but the very act of looking causes the cake to instantly collapse. Because of this massive constraint, your code tests have to be probabilistic by design. You have to rely on statistical assertions, property-based invariants, and those small instance simulators we just talked about.
Once your code is constructed and validated, we hit stage 3, compilation and transpilation. And man, this is the heart of the hardware constraints. This is where your elegant, mathematically perfect source code violently collides with noisy physical reality.
The compiler pipeline is essentially a brutal series of contortions. First, it's got to rewrite your high-level source code into the specific, limited basis gates that your target device actually supports. Second, it maps your beautiful virtual qubits onto the messy, physical hardware qubits. Third, and this is a huge bottleneck, it routes operations through the device's specific connectivity graph, which usually means inserting a ton of swap operations if your qubits aren't physically sitting next to each other.
Finally, it desperately tries to optimize and reduce the 2-qubit gate count and overall circuit depth. A circuit that looks totally shallow in your source code, it might explode in depth once the transpiler maps it, which means your entire program could suddenly just get eaten alive by decoherence noise.
To put this in perspective, just look at how two major hardware modalities totally change the game. If you're targeting superconducting qubits, you're dealing with sparse, nearest neighbor grids. The routing impact is massive. The compiler has to insert a heavy amount of swap gates just to get distant qubits to talk. But if you switch over to target trapped ions, you generally get all-to-all connectivity. That means way less swap overhead. However, the compiler now has to map to entirely different native gates with completely different execution speeds. The compiler isn't just translating your code anymore, it is acting as a fundamental defining part of the algorithm itself.
Because of this massive hardware diversity, the whole ecosystem relies heavily on intermediate representations, or IRs, to keep from just totally fragmenting. We use things like OpenQSM3 to manage circuit-level descriptions, explicit hardware timing, and pulse control. Alongside that, we've got QIR, which is an LLVM-based compiler representation. These IRs are absolutely vital. They're the bridge that allows different front-end quantum languages to actually interact with completely different back-end hardware platforms without losing all that critical execution metadata.
All right, so we've formulated, we've constructed, and we've compiled. Now we arrive at stage 4, hardware execution and jobs. It's time to actually run this probabilistic experiment on the QPU.
Now keep in mind, in the near term, we don't just run an app on a quantum computer. We rely entirely on an architectural pattern called hybrid quantum classical computing. The QPU basically acts purely as an accelerator. It evaluates specialized subroutines to generate samples, while a classical processor sits next to it, doing all the heavy lifting, handling the optimization, preparing inputs, validating results, and batching the jobs together.
And this brilliantly illustrates how we actually get jobs onto the hardware today. You don't just send raw circuits anymore. You use execution mechanisms known as primitives. You've got samplers, which you use when you need to return sampled bit string distributions from your circuits. And you've got estimators, which you use when your algorithm needs to compute the expectation values of specific observables, which, by the way, is foundational for stuff like quantum chemistry or variational algorithms. You submit these primitives via cloud APIs or runtime sessions to keep that hybrid loop highly efficient.
Which brings us to our final stage, post-processing and iteration. Because, let's be real, running a job once is almost never the end of the story. A quantum program is an iterative statistical experiment, not a one-and-done deterministic script.
When the QPU finally sends data back to your classical host, you're looking at extracting a massive variety of statistical outputs. You've got your raw counts, bit string samples, expectation values, sure, but you're also pulling uncertainty estimates. You're applying complex error mitigation outputs to computationally suppress the physical noise you just experienced on the hardware. And then you're feeding all of this back into classical optimizer updates to prep for the next run.
And since early results are almost always super noisy or inconsistent, you inevitably enter this grueling iteration loop. You systematically tweak parameters. You might have to change the ansatz or adjust your measurement grouping to save precious QPU time. You might alter how the problem is embedded on the hardware graph, tweak the transpilation settings, or completely switch your backend hardware if the calibration drifted. Or maybe just modify your shot allocation to reduce variance. It is a constant, rigorous merging of your source code with statistical analysis and hardware metadata.
So, when you finally finish this entire rigorous journey, from the very first mathematical formulation to the final extracted data, every serious quantum engineer is left looking at their evidence with one final provocative question. Is a quantum subroutine truly the right tool for this specific problem? And more importantly, do your reproducible statistical confidence intervals actually prove it against the absolute best classical baselines? Answering that question honestly, well, that's the true core of modern quantum programming.
We're going to explore the quantum software landscape today, but we're looking at it through a very specific lens. We're treating this whole space as a layered engineering ecosystem rather than some winner-take-all language contest. You know, if you follow quantum computing, you've probably seen the endless, heated debates about which single language is going to completely dominate the field. But here's the thing. As we transition from theoretical physics into rigorous software engineering, that's just not how this technology works.
Okay, let's dive into this. To build real practical applications for these machines, we really have to abandon the idea of just writing a faster classical program. Quantum programming is, at its core, a massive engineering stack. It's this deep, intricate combination of linear algebra, software design, advanced compilers, severe hardware constraints, statistical analysis, and complex cloud workflows. You're not just writing code,
You are literally orchestrating an incredibly delicate state preparation and measurement experiment.
In this explainer, we'll take a highly structured tour. Number 1, why this isn't a language contest. 2, circuit and hardware-aware stacks. 3, hybrid, cloud, and high-performance computing frameworks. 4, compilers and resource planning. 5, the annealing paradigm. And finally, number 6, how to actually choose the right stack for your specific goals.
Let's hit section 1, not a language contest. Before we start comparing specific tools, we absolutely must evaluate these stacks based on strict engineering rubrics rather than just industry hype. When we look at a software development kit, an SDK, we need to ask some hard questions. What's its primary abstraction? Are we building circuits, or are we solving energy models? What's the host language style? What target hardware and simulators does it natively support? How mature is the ecosystem? And ultimately, what is its absolute best fit workflow?
Right now, when you write code for current NISQ devices, those noisy intermediate-scale quantum machines, your hardware constraints dictate literally everything. You are severely limited by qubit count, circuit depth, connectivity, and calibration drift. Because of these intense constraints, practical programming is dominated by resource awareness. It's kind of like trying to solve a complex sliding puzzle on a very strict deadline. For example, on a sparse superconducting chip, how you route your qubits can radically change your overall circuit depth. And what that means is, the compiler isn't just some back-office translation tool anymore. The compiler is essentially part of the algorithm itself.
Moving into section 2, circuit and hardware-aware stacks. This is the foundational gate model paradigm.
And this brilliantly illustrates the massive philosophical differences between these ecosystems. On the left, we've got Qiskit, backed by IBM. Qiskit is arguably the strongest all-around choice out there today for gate model circuits. It's deeply integrated with IBM hardware, and it abstracts workflows beautifully through powerful primitives like the sampler and estimator. Plus, it features a highly advanced transpilation pipeline, which actually rewrites your input circuits to perfectly match the target device's topology. On the right, though, we have Cirq from Google Quantum AI. Cirq is intensely hardware-aware. Instead of hiding those pesky hardware constraints, Cirq surfaces them right to the programmer. It represents circuits as a collection of moments, which are basically operations acting on qubits during specific, abstract time slices. If you're doing really granular calibration-aware research, where you absolutely need tight control over routing and device objects, Cirq is an incredibly capable research stack.
Okay, section 3, hybrid, cloud, and HPC. Let's look at mixed orchestration workflows.
So, most near-term algorithms require a really tight loop between classical CPUs and quantum processors. Here we have PennyLane, Amazon Braket, and CUDA-Q. And these three serve completely different architectural needs. PennyLane is all about differentiable programming for machine learning. Braket is your multi-provider cloud execution layer. And CUDA-Q? That's built for heterogeneous, high-performance classical and quantum integration. Let's break these down one by one.
First up, PennyLane. Developed by Xanadu, this framework treats quantum programming in a fundamentally different way. It's built entirely around differentiable quantum programming. What does that mean? Well, it treats quantum circuits as trainable, differentiable functions sitting inside a larger computational graph. You actually use classical gradient descent algorithms to optimize parametrized quantum gates. If you're working on quantum machine learning, variational quantum eigensolvers, or hybrid chemistry models, PennyLane's unique ability to seamlessly integrate with classical machine learning workflows makes it an absolute powerhouse.
Amazon Braket, on the other hand, acts as a comprehensive cloud operations layer. Its greatest strength is its totally hardware-agnostic approach. Through one single API, Braket gives you managed access to superconducting processors, trapped ion systems, and even neutral atom hardware. But what's really vital to understand here is that Braket doesn't just support standard digital circuits, it also supports analog Hamiltonian simulation. That allows you to program by specifying time-dependent energy parameters. It seamlessly manages the provisioning of classical resources for your hybrid loops and then releases them the second the job is done.
Then we have the framework bridging the gap between quantum and mainstream supercomputing, CUDA-Q from NVIDIA. CUDA-Q provides a heterogeneous programming model in C++ and Python that seamlessly delegates your workloads right across CPUs, GPUs, and QPUs. If your workflow relies heavily on accelerated simulation, or if your quantum kernel is really just one piece of a massive scientific application running on a supercomputer, CUDA-Q is the exact toolchain designed for that high-performance integration. Section 4, Compilers and Resource Planning. This is all about solving those frustrating bottlenecks. Now, what's really interesting here is that sometimes the front-end language isn't actually the challenge at all. It's how efficiently you can map your logic down to the hardware. That's where TKit comes in.
Developed by Quantitunium, Qiskit isn't focused on being your primary application interface. Instead, it acts as a dedicated, highly optimizing compiler and a cross-backend conversion layer. When you're fighting against decoherence and every single extra 2-qubit gate introduces more errors into your system, your compilation quality literally becomes your main bottleneck. Qiskit is incredibly valuable for routing, placement, and optimizing your circuits so they run as efficiently as humanly possible across a wide variety of different hardware platforms.
Similarly specialized, but in a totally different way, we have Q# and the Microsoft Quantum Development Kit. Q# is a dedicated domain-specific language designed purely for quantum logic. While it definitely can build near-term circuits, where it truly excels is in algorithm pedagogy and resource estimation for the fault-tolerant era. Let's say you're trying to figure out exactly how many physical qubits, logical clock cycles, and magic state distillation factories you're going to need to run a massive algorithm like Shor's. The Azure Quantum Resource Estimator integrated into Q# is basically unmatched for that kind of deep architectural planning.
Moving on to Section 5, the annealing paradigm. This is a massive shift away from everything we just talked about.
Right, so everything we've discussed up to this point assumes we're building sequences of gates. But in the annealing model, you do not write circuits at all. Instead, your source code object is an energy model. You actually formulate your problem as an Ising model or a quadratic unconstrained binary optimization problem, a QUBO. The hardware then naturally evolves toward the lowest energy state, and that state represents a solution to your problem. It is a completely different mental model for programming.
And the go-to primary stack for this paradigm is D-Wave Ocean. Ocean is designed specifically to help you map discrete optimization problems onto D-Wave's annealing hardware topologies. The compilation problem here isn't about routing gates. It's a process called minor embedding, which basically means fitting your logical problem graph into the physical hardware graph. I cannot state this clearly enough. Ocean is absolutely not a substitute for a circuit SDK. It is a highly specialized, mature stack built for a completely different programming model.
Finally, Section 6, choosing the right stack. Let's see how all of this builds into a practical decision map.
Let's rapid-fire map your specific goals directly to the recommended stack. If your center of gravity is IBM hardware, circuit transpilation, and you want strong educational resources, you start with Qiskit. If you're doing really granular hardware-aware circuit research that requires deep, low-level device control, Circ is for sure your best fit. If your project relies on differentiable programming, quantum machine learning, or hybrid workflows, PennyLane is unmatched. And if you need multi-provider cloud execution and you want to test across superconducting, ion trap, and analog hardware all from a single script, you use Amazon Bracket.
Continuing that map, if your problem naturally translates into an Ising or QUBO optimization model, you are officially in the annealing paradigm, and you use D-Wave Ocean. If your main goal is algorithm pedagogy or running complex resource estimations to plan for future fault-tolerant machines, you reach for Q#. If your circuits are failing due to routing bottlenecks and you need heavy-duty, cross-platform compilation optimization, you integrate TCAT into your pipeline. And finally, if you are integrating quantum acceleration into a massive, heterogeneous supercomputing application, CUDA-Q is the toolchain you need. So, the crucial point is this. Ultimately, the practical question for software engineers is not the hype-driven, which quantum language is best. The real mature question is, which stack matches the target problem, the available hardware, and my specific engineering workflow? Quantum programming is just this rich, incredibly layered ecosystem of specialized tools. As we move forward, this ecosystem is only going to get deeper and more complex. We are rapidly transitioning from raw physical experiments to robust, fault-tolerant software engineering. The tools exist today to start building and simulating at a massive scale. So as you design your own algorithms and map out your own engineering pathway, which layer of the quantum stack will your next application rely on most?
Beneath the wildly different syntax of various quantum software development kits, or SDKs, lies a completely universal engineering workflow. In this explainer, we are demystifying quantum programming by looking at the concrete, beginner experience of writing your very first quantum code.
Here is our roadmap for today. We'll start with the universal quantum workflow, compare a basic Bell state across different SDKs, and then scale up to hybrid VQE orchestration. After that, we'll explore non-circuit workflows, bridge the gap with compilers, and finish up with the absolute golden rule, validation.
Section 1. The Universal Quantum Workflow. Same engineering, different nouns.
It literally doesn't matter if you're writing in Qiskit, Circ, or Bracket, because this 5-step loop applies universally. You will always 1. Define your variables or qubits. 2. Build your circuit, kernel, or model. 3. Choose your backend or simulator. 4. Run your shots or samples. And 5. Collect and validate the data. You see, quantum programming isn't just writing a faster deterministic function. It is essentially a highly structured state preparation and measurement experiment. Section 2. Bell state across different SDKs. The Quantum Hello World.
Let's look at the Rosetta Stone of quantum programming. Building a simple entangled Bell state is our baseline across the major circuit-oriented stacks. We're talking about a 2-qubit circuit that applies a Hadamard and a controlled NOT gate to create perfectly correlated samples, ideally returning the bit strings 0, 0, and 11. Crucially, a Bell state acts as your immediate sanity check for your gates and correlation analysis before you accidentally turn a $1 million quantum processing unit into a very expensive random number generator.
It is fascinating to look at how different SDKs explicitly map the exact same concepts to their own specific syntax nouns. For example, Qiskit builds a quantum circuit, applies H and CX, and then samples or estimates results. Circ creates explicit qubit objects, builds a circuit with H, CNOP, and measurement, and then runs repetitions. PennyLane, on the other hand, wraps operations inside a Q node for differentiable programming, returning counts or an expectation value. Meanwhile, Q-sharp expresses operations natively using allocated qubits. The core engineering idea is perfectly identical, the spelling is just different.
Taking this a step further, Bracket builds from cloud-managed execution objects. You build a circuit, attach measurements, choose a simulator or cloud device, and submit a task. Compare that to OpenQASM3, which represents the exact same concept much closer to the metal. It's a portable, assembly-style program with explicit qubit and bit registers, mapping out the identical H, CX, and measure statements.
Section 3. Scaling up the VQE loop, modern hybrid orchestration.
Moving past simple circuits, we find that modern quantum programming is actually a hybrid classical quantum orchestration. This is best illustrated by a minimal variational quantum eigensolver, or VQE, pattern. The loop basically has 4 steps. Prepare a parameterized ansatz, estimate an observable like a Hamiltonian, update the parameters classically, and record the metrics. Think of this as setting up a heterogeneous CPU and GPU kernel, but here, the quantum processing unit estimates energy expectation values while your classical computer updates the parameters until convergence.
Whether you're using Qiskit, PennyLane, Bracket, or CUDA-Q, this conceptual loop dictates your choices. You absolutely need a Hamiltonian made from polyterms, a parameterized ansatz built with rotations and entangling gates, and expectation value calls instead of just raw bit strings. The syntax might vary, but the rigorous statistical constraints of this hybrid loop remain universally the same.
Section 4. Beyond circuits, annealing, analog, first-class non-circuit workflows.
Now let's completely shatter the idea that quantum programming only means drawing gates. Take D-Wave's Ocean SDK for quantum annealing. Here, you define a binary quadratic model, an Ising model, or a QUBO. You choose an exact, classical, hybrid, or annealing sampler, and you inspect energies. You don't use gates for analog Hamiltonian simulation either. Instead, you specify physical parameters, things like atom positions, detunings, amplitudes, interactions, and time schedules. Make no mistake, these are first-class quantum programming workflows, not just alternative spellings of circuits.
Section 5. Bridging software and compilers, the glue of the heterogeneous ecosystem.
CUDA-Q is a prime example of a syntax bridge in this space. It's an open-source C++ and Python toolchain that embeds a quantum subroutine, called a kernel, directly into CPU, GPU, and QPU workflows. The host code launches the quantum kernels and collects the sample or expectation results. Architecturally speaking, a quantum program is fundamentally just another classical accelerator subroutine bridging into high-performance computing. Right beneath that high-level Python code, we rely on intermediate representations. OpenQASM3 acts as a portable representation that's closer to a readable circuit assembly, managing explicit timing, pulses, and dynamic circuits. Then you have QIR, or Quantum Intermediate Representation, which sits much closer to the heavy-duty compiler infrastructure. It's LLVM-based, language-agnostic, and hardware-agnostic, allowing front-end code to interface seamlessly with back-end execution. Section 6. The Golden Rule, Validation. Code that runs isn't code that works.
Let's confront the absolute most critical reality check of quantum programming. Your first program ran without crashing, But how do you know it actually worked? Because quantum states cannot be freely inspected without measurement, and because hardware is inherently noisy, we have to practically validate these first programs under severe, limited observability. You have to aggressively cross-check your outputs using essential validation techniques. For a Bell state, you validate that your expected samples are mostly 0, 0, and 1, 1. For an expectation value workflow, you compare your results against a small, exact simulator. For an ocean optimization model, you ensure low-energy samples practically satisfy the intended problem. And for analog schedules, you compare measured correlations against theoretical expectations. Learning syntax is really just the entry point. Serious quantum programming means understanding your model choice, back-end constraints, and statistical output to ensure you are seeing actual physics and not just hardware noise.
Quantum software engineering is closer to experimental scientific computing than conventional deterministic application programming. So here is a question to leave you with. Does your current classical coding mindset fully prepare you for a world where learning syntax is just the entry point to reproducible statistical quantum experiments?
All right, let's dive right into this explainer and unpack the rigorous engineering stack that transforms abstract quantum algorithms into executable physical hardware instructions. Because, you see, when you write quantum code, you aren't just writing a faster version of an ordinary program. You are actually defining a highly specialized computational kernel. And the heavy machinery that translates that mathematical kernel all the way down to analog microwave pulses or precise laser interactions, well, that is what we call the compiler pipeline. Here is our roadmap for this explainer. First, we'll look at the translation bottleneck. Second, intermediate representations. Third, the compiler pipeline itself. Fourth, the 2026 software ecosystem. And finally, surviving hardware constraints. Let's start with Section 1, the translation bottleneck, and the very real problem of ecosystem fragmentation. So, picture this. We really have to ask ourselves, how does a program written in a high-level SDK, like Qiskit, PennyLane, or Q#, possibly execute across entirely distinct physical modalities? It's kind of wild when you think about it. We have superconducting circuits using microwave pulses over here, trapped ions using laser gates over there, and neutral atom arrays doing something completely different. Each one of these requires entirely different native instructions and timing to actually work.
And this perfectly illustrates what's known as the N times M problem. Without a unified approach, every single time a new language or a new hardware target is created, developers would have to sit down and write a completely separate custom-built translation path. You multiply N languages by M hardware targets, and you get absolutely unsustainable engineering chaos. It just doesn't scale.
Moving right along to Section 2, Intermediate Representations, or IR, basically the universal translator. To solve that chaos, we use an IR. An intermediate representation acts as a universal translator right in the middle, effectively decoupling the software you write from the specific hardware it's going to run on. It bridges high-level semantic meaning and low-level hardware execution. So if you're a front-end developer, you can focus purely on the math and the algorithms, while the back-end engineers can focus purely on hardware optimization. It's a total game changer. Now let's look at the direct contrast between the two dominant approaches out there today, OpenQASM3 and QIR. OpenQASM3 is much closer to readable quantum assembly. It focuses heavily on the explicit circuit itself. We're talking real-time classical control flow, explicit hardware timing, and pulse-level descriptions that are absolutely crucial for dynamic circuits. On the flip side, QIR is much closer to a traditional compiler IR. It builds directly on classical LLVM infrastructure, which is huge. It lowers quantum operations into LLVM-style functions and handles really complex quantum classical control. By treating qubits abstractly as opaque pointers, QIR lets your quantum programs immediately leverage literally decades of classical compiler optimization. Let's move to Section 3, the compiler pipeline, getting from code to the QPU. Okay, let's step through the actual journey your code takes. You start with your high-level SDK code. That code then drops into an intermediate representation, often using MLIR-style multi-level optimizations to refine the logic at various abstraction layers before moving on. Next, the compiler decomposes that abstract circuit, maps the logical to physical qubits for layout and routing, and figures out the precise scheduling. From there, it performs native gate lowering, translating your generic gates into highly specific hardware instructions under incredibly strict timing constraints. And finally, it hits runtime execution for measurement and classical processing.
Now for Section 4, the 2026 Software Ecosystem, where we look at some major pipeline advancements.
The engineering leaps we're seeing here are massive. For example, Qiskit has moved its performance-critical DAG manipulation directly into Rust. They've expanded their CAPI and improved QPY serialization. All of this drastically speeds up compilation and opens up staged optimization paths toward Clifford plus T fault-tolerant instruction sets, which is exactly where reducing T-count matters most. Meanwhile, PennyLane introduced the Catalyst QJIT compiler path to seamlessly handle dynamic, hybrid classical, and quantum control flow at scale. TCAT has established itself as a highly aggressive platform-agnostic optimizing compiler layer. And over at Microsoft Azure, they're using Q# and QIR inputs to run rigorous resource estimation for future fault-tolerant architectures.
Finally, Section 5, Surviving Constraints. Time for a dose of hardware reality. Because the truth is, every single circuit has to survive a brutal gauntlet of physical constraints. Think about it. If your algorithm uses a gate that simply isn't native to the hardware, the compiler has to expand it, which bloats your circuit depth. If your hardware uses a sparse lattice topology, like we see in many superconducting chips, the compiler has to constantly insert swap gates just to route qubits around, which is very different from trapped ion systems that might offer all-to-all connectivity. Add in the calibration drift that changes qubit quality from day to day, the measurement overhead, and the ever-ticking clock of noise and decoherence limits, and you quickly see why this compiler stack is so vital.
This brings us to a crucial takeaway. Your compiler is not just some back-office translation tool. It's a survival filter. It is the decisive engineering layer that determines if your abstract mathematics can successfully map to the physical universe and actually return an observable result before the whole system decoheres.
And that leaves us with a really critical mindset shift for any serious developer navigating the space. You can no longer afford to just think about asymptotic complexity on a whiteboard. You have to think about routing overhead, gate expansions, and noise exposure. When you sit down to write quantum code today, are you merely expressing mathematical logic, or are you engineering a physical experiment designed to survive the real world?
Let's completely shatter a really common illusion right out of the gate. When we first dive into quantum algorithms, we're usually taught using these elegant, hardware-agnostic mathematical models, right? It's this pristine world of perfect state vectors and beautifully clean, discrete unitary matrices. But here is the brutal reality. That beautiful math absolutely does not translate directly into execution. What we're actually dealing with in the noisy intermediate-scale quantum, or NISQ era, is basically a rigorous engineering obstacle course. Hardware constraints completely dominate software design.
Think about the massive contrast between abstract source code, neat, concise, and logically perfect, and the post-transpilation circuit. This post-transpilation circuit is the messy, bloated, chaotic reality of what actually gets mapped to a physical quantum processing unit, or QPU. The transpiler literally has to twist, stretch, and bloat your elegant code just to make it physically survivable for the machine. Understanding this huge gap, that is the entire essence of hardware-aware programming. To conquer this obstacle course, we are going to systematically break down the core constraints. 1. Native gates. 2. Connectivity and routing. 3. Depth, time, and coherence. 4. The measurement bottleneck. 5. Calibration drift. And 6. The post-transpilation checklist.
Let's jump straight into native gates and how we actually translate to the physical QPU.
So you might write your algorithm using whatever gates are mathematically convenient for you. But honestly, the hardware simply doesn't care. It only understands its native gates. That's the specific, highly limited hardware instruction set supported by your target QPU. For instance, a trapped ion system might only expose GP gates or Mulmer-Sorensen interactions. Superconducting processors have their own entirely distinct fixed operations. So the compiler is forced to translate your convenient abstract gates into this very limited physical basis. It's an absolutely mandatory translation process.
And here's exactly why that matters. The number 3. Decomposing just a single abstract gate from your source code can frequently inflate the executed circuit by 3 or more native operations. Why is that such a big deal? Well, because every single gate you execute introduces a tiny bit of physical error. By simply translating your code into the hardware's native language, the compiler drastically inflates the circuit size. You're basically multiplying your program's exposure to operational errors before the computation has even really begun.
Which brings us to connectivity and routing, the brutal reality of moving quantum information.
Once we actually have the right language,
We have to deal with physically moving, incredibly fragile quantum information across a microchip. Quantum hardware usually doesn't allow every pair of qubits to interact directly with each other. If your algorithm requires a 2-qubit gate between 2 distant logical qubits, the compiler literally has to manually move those quantum states next to each other. It does this through swap insertion. This is a crazy, costly process of injecting extra operations just to shuffle data across unconnected physical qubits. For poorly mapped circuits, these injected swap gates can massively inflate your circuit depth, adding catastrophic layers of noise.
And this routing pressure changes entirely depending on the machine you're using. Superconducting chips typically have sparse, fixed lattice connectivity. That means heavy routing and massive swap insertion overhead. By contrast, trapped ion systems boast all-to-all connectivity. Sounds great, right? No swaps? But their gates are physically slower. So the compiler has to hyper-focus on gate times and scheduling instead. And for quantum annealers, the routing problem transforms entirely into an embedding problem, where you actually have to force your logical problem graph to literally fit the specific hardware topology. Your compilation strategy is completely dictated by the physical chip.
Next up, we have depth, time, and coherence, the ultimate race against the clock.
Decoherence is the rapid decay and loss of your fragile quantum states to the surrounding environment. Because of this, circuit depth, which is the number of sequential gate layers, and the scheduled duration of your program are absolutely critical cost metrics. Deeper, longer circuits occupy the device for more time. Every microsecond that ticks by, your program is accumulating decoherence from the environment, plus operational errors from the imperfect gates themselves. It's a literal race against the clock.
When we analyze error impact by operation type, it reveals a pretty stark reality. Single qubit gates, they have a relatively low impact, but 2-qubit gates are significantly higher, and swap operations, which are actually made of multiple 2-qubit gates, are critical. What you really need to take away from this is that your 2-qubit gate count is the true defining cost metric of your program. Source code elegance means absolutely nothing if your post-transpilation depth and 2-qubit gate counts are off the charts.
Let's move to the measurement bottleneck and how we actually extract statistical truth.
Assuming your circuit actually survives the clock, we hit our next massive constraint. We need to completely debunk the myth of the deterministic output. A single run of a quantum circuit normally gives you just one single classical bit string outcome. But practical algorithms, like the ones used in quantum chemistry, are actually designed to estimate observables. They don't just print out one final deterministic answer like a classical calculator. Instead, measurement is this highly intensive, wildly costly statistical campaign.
Let's walk through the rigorous statistical workflow required just to get an answer out of the machine. First, basis rotation. You have to actively rotate your qubits before measuring so you can look at different axes. Second, shot allocation. You actually must run the circuit hundreds or thousands of times to gather enough statistical samples. Third, polygrouping. Grouping compatible measurement terms together to save QPU execution time. And finally, expectation estimation, managing the statistical variance to find your actual answer. So measurement isn't just reading a variable, it's a first-class operational bottleneck.
So, okay, you've compiled your native gates, you've routed your swaps, beat decoherence, and managed your measurement statistics. Your program works perfectly on Tuesday. But what happens when the hardware itself changes overnight?
That brings us to calibration drift and navigating this constantly shifting hardware landscape.
We really have to realize that the quantum processing unit is not a static piece of silicon. It is a shifting, living landscape of physical phenomena. Calibration drift is the continuous, daily fluctuation of back-end properties. Qubit error rates, readout fidelities, coupler performance, they constantly change. A circuit that you meticulously mapped to a set of perfect, high-performing qubits yesterday might suddenly fail today just because those exact same qubits have drifted and become noisier. Hardware-aware programming means you can never, ever assume your back-end's behavior is permanent.
Let's trace this out on a timeline. On day 1, you've got a baseline calibration. Everything looks great. By day 2, you start seeing shifting gate fidelities. Day 3, maybe there's a sudden spike in readout errors due to thermal fluctuations. And by day 4, the entire chip might require recalibration. This perfectly illustrates why keeping historical calibration records and runtime metadata is absolutely vital. If you don't track the exact hardware state at the exact moment your code ran, your quantum experiments will be completely irreproducible.
Finally, the post-transpilation checklist. This is your engineering defense.
Because we are navigating this aggressive physical obstacle course, we have to arm ourselves with the right metrics. If there is one core philosophy to take away from this entire explainer, it is this: never trust your source code.
The code you write on your laptop is practically a fiction. The transpiled circuit, the one that has been expanded, routed, and mapped to drifting qubits, is the only circuit that matters.
So, here is the definitive checklist you must inspect to ensure your mathematically correct algorithm is actually executable. You must check your final gate counts, hyper-focusing on those expensive 2-qubit gates. You need the exact circuit depth and scheduled execution time. You absolutely must verify the physical layout and the coupling map chosen by the transpiler. Check your measurement groups. Always archive the back-end calibration records from the exact hour you ran the job. And finally, meticulously separate and report your raw outputs versus your mitigated outputs.
There's a quote from the sources that sums this up perfectly. Quantum software engineering is closer to experimental scientific computing than conventional deterministic application programming. You aren't just writing a script here, you're configuring a rigorous physics experiment involving software, statistics, and extreme hardware constraints.
And that means we have to completely elevate how we view the compiler. The compiler is not some back-office translation tool that you can just ignore, because it makes life-or-death decisions about swap insertions, native basis translation, and qubit selection. The compiler actively dictates the ultimate design and success of your program. It is a fundamental part of your algorithm.
Which leaves us with a final, kind of provocative thought to ponder. If your compiler is forced to radically alter, bloat, and rearrange your elegant circuit just to survive the harsh realities of the hardware, whose code is actually executing on that processor? Yours or the machine's? Mastering quantum programming means taking back that control by deeply understanding the hardware. In this segment of our explainer, we are confronting a really crucial baseline. Physical hardware readiness is ultimately a rigid software constraint. You know, when we talk about quantum programming, there's always this temptation to treat it kind of like classical software, where the physical hardware is neatly hidden away behind a massive wall of abstraction. But honestly, that is fundamentally not the reality of quantum computing today. The specific device you choose literally alters the code you write.
Our roadmap for this segment covers the hardware readiness checklist, superconducting qubits and routing, trapped ions and connectivity, neutral atoms and analog, diverse platforms like photonic, spin, and NMR, and we'll wrap up with cloud-native quantum infrastructure.
All right, let's jump straight into Section 1, the hardware readiness checklist. Because before a single line of code can run, the physical system has to clear some major hurdles.
People sometimes treat the famous De Vincenzo criteria like dusty historical artifacts from the year 2000, but actually, they act as a highly rigorous, totally modern checklist dictating what your code can actually achieve. The first 3 requirements define your absolute baseline of operation. First up, your system must have scalable, well-characterized qubits. Second, you absolutely must be able to reliably initialize them to a known fiducial state, like the 0 state. And third, the coherence times, basically how long the qubits hold on to their delicate quantum state, have to be significantly longer than the time it takes to actually perform your gate operations.
This maps out the direct, unavoidable link between physical traits and your compiler. Think about it. Initialization quality directly dictates your state preparation and reset assumptions in the software itself. If you can't reliably initialize, well, your programmatic starting point is fundamentally flawed right out of the gate. Likewise, coherence and gate fidelity put a hard ceiling on your circuit depth. If your qubits decohere rapidly, your compiler literally has to ruthlessly optimize for shorter, shallower schedules, completely regardless of how elegant your original source code is.
Let's look at the final 3 criteria, which shift our focus from the qubits themselves over to operations and control. You need a universal native gate set, or at the very least, a credible compilation path to one, so your compiler can approximate any unitary operation. You also absolutely need high-fidelity measurements to pull reliable statistics out of the system. And finally, and this is absolutely crucial for modern error correction, you need a super-fast, highly reliable classical control interface. That classical computer has to sequence instructions and decode errors in real time.
So, what does this all mean? It means hardware readiness is a software constraint. Period. The quality of your native gates shapes your compiler targets. The quality of your measurements determines your readout error and the confidence intervals of your final statistics. And that fast classical feed-forward interface? That literally dictates whether your advanced dynamic circuits, your qubit reuse strategies, and your quantum error correction loops will function at all. If the hardware cannot feed classical data forward fast enough, those advanced software abstractions simply fail.
Moving on to Section 2, superconducting qubits and routing. Let's see how these exact constraints manifest in the most common gate model platform we use today.
Superconducting processors, like the ones developed by IBM and Google, utilize microwave-controlled circuits that are usually arranged in a lattice-like chip geometry. This physical layout features fixed or topology-dependent coupling maps. In plain English, your qubits can only directly interact with their immediate physical neighbors. Because of this, the physical map completely governs the transpilation process. It turns compilation into this massive, complex routing puzzle.
Let's break down the specific software bottlenecks here. Sure, superconducting qubits offer very fast nanosecond scale gate operations, which is awesome, but they come with some heavy baggage. We're talking massive cryogenic infrastructure and severe crosstalk concerns between those neighboring qubits. Plus, calibration drift means a layout that ran perfectly yesterday might be way too noisy today. But the biggest software hurdle for sure is the severe routing constraints. If your code needs to entangle two qubits on total opposite sides of the chip, the compiler has to insert multiple swap operations just to move the information across the lattice. This swap overhead drastically inflates your circuit depth and exposes the whole run to more noise.
Section 3. Trapped ions and connectivity. Here is where we see how changing the physical structure completely alters the compilation math.
Let's contrast these two paradigms. We just saw how superconducting lattices suffer from heavy routing constraints and massive swap overhead. However, trapped ion systems like the ones from IonQ or Quantum use lasers to interact with ions held in a trap. Because these ions can interact globally, these systems boast incredibly long coherence times and make claims of all-to-all or fully connected topologies. For a developer, this is a real game changer. You don't have to suffer that heavy swap penalty just to entangle distant qubits.
But we always have to look at the trade-offs, right? High connectivity absolutely reduces swap insertion, but trapped ions are not a magic bullet. They face their own major compilation hurdles. For one, their gate times are significantly slower than superconducting gates. Also, native operations still require heavy decomposition down into the device's specific basis gates. This introduces highly complex scheduling requirements for the compiler. And those slower execution speeds mean you face completely different queuing trade-offs when you're running jobs on the cloud. You are basically trading one set of compiler constraints for another.
All right, Section 4, Neutral Atoms and Analog. Get ready because this modality represents a massive paradigm shift.
Consider this idea. In analog workflows, the program is a physical Hamiltonian schedule rather than a gate-by-gate circuit. If you're using neutral atom hardware for analog Hamiltonian simulation, you essentially have to throw away the whole concept of discrete digital circuits. You are no longer writing a circuit, you are programming a continuous time-dependent and space-dependent physical schedule. It's a totally different way of thinking.
This is entirely possible because neutral atoms can be arranged using optical tweezers into highly flexible, programmable geometries. The computations are controlled by driving Rydberg interactions, detunings, and amplitudes over time. The software problem here isn't routing. It's embedding your logical problem directly into the physical spatial layout of the atoms themselves. It is incredibly powerful for simulating many-body physics and is actually becoming increasingly relevant for emerging fault tolerance roadmaps due to its flexible connectivity. But again, it demands an entirely different programming abstraction.
Let's move to Section 5, Photonic, Spin, and NMR. We need to touch on these diverse platforms to get the full picture.
These platforms are a great reminder that we shouldn't just assume the standard gate model will be the only physical paradigm forever. Photonic systems, for example, often favor cluster states and networking, leaning heavily into measurement-based computation, rather than just applying sequential gates. From a software perspective, this means your compiler and your intermediate representations need to be perfectly equipped for measurement-heavy workflows and serious loss management, rather than standard qubit routing.
We also definitely need to note nuclear magnetic resonance, or NMR-style systems. While there are commercially available room-temperature NMR quantum computers that utilize atomic spin states, it is crucial to position these accurately. They are strictly instructional or local research platforms. They are absolutely excellent for education and learning the ropes, but they are not general, scalable production targets for commercial enterprise workflows.
Finally, Section 6, Cloud-Native Quantum Infrastructure. Given all the extreme cryogenic and laser infrastructure required to run these things, how do developers actually access these machines? The answer is the cloud.
Out in the wild, there are two main deployment models. On one hand, we have hyperscaler aggregators like Amazon Braket and Azure Quantum. These platforms give you a unified SDK and route your jobs out to multiple third-party hardware vendors. They offer incredible hardware-agnostic flexibility. On the other hand, we have single-vendor platforms like IBM Quantum, which route jobs strictly to their own proprietary hardware.
Now, while you do lose that cross-platform flexibility, you gain incredibly deep platform-specific access to advanced transpilation and runtime primitives.
So, what does a quantum engineer's daily workflow actually look like? Well, in practice, you basically never start on real hardware. You always start with local simulators for initial debugging. Then you might graduate to on-demand, high-performance cloud simulators. When you are finally executing on actual QPUs, you'll utilize managed hybrid jobs or runtime sessions to handle that constant, rapid back and forth between classical and quantum processors. You have to actively manage queuing times, and, this is absolutely critical, you must collect not just your result bit strings, but all the hardware metadata like calibration timestamps so you can actually reproduce and understand your results later.
When we look at source-reported hardware roadmaps, we definitely have to navigate carefully and avoid getting caught up in the hype. In the near term, the focus is squarely on resource-aware execution and exploring platforms like neutral atoms. Looking to the midterm, we are seeing the development of more capable generations and long-range couplers, like IBM's experimental architectures designed to connect non-adjacent qubits. This is all meticulously building towards the long-term goal of early fault tolerance. The software stack is frantically trying to build the resource estimators and error decoding loops required to actually make this timeline a reality.
Let's wrap this up with a really crucial question. If your hardware choice fundamentally changes your programming abstractions, your compilation bottlenecks, your validation methods, and literally even your performance metrics, what does that make the future quantum software engineer? The reality we're facing is that quantum programming is not just writing software. It is a full engineering stack, combining advanced math, compiler design, statistics, and a really deep understanding of physical hardware constraints. The successful developer of the future won't just be a coder. They will have to be a truly hybrid engineer.
Let's dive right into this explainer and completely demystify quantum programming. We're going to treat this not as some abstract, theoretical physics concept, but as a rigorous software engineering discipline built on modular, highly reusable design patterns. By wrapping our heads around these repeating patterns, you'll see how quantum programming is actually a deeply integrated engineering stack, one that combines math, software, compilers, and some incredibly strict hardware constraints.
To build that intuition, we'll be progressing sequentially through a sort of pattern library. We'll start with the Bell state sanity test, move on to basis rotation measurement, tackle parameterized ansatzes, break down the compute-use-uncompute pattern, look at batch execution and observable grouping, and then tie it all together with a minimal VQE workflow.
All right, starting off with Section 1, the Bell state sanity test, which is essentially the hello world of quantum entanglement.
So before you can run any complex algorithm, you have to know if your hardware is actually behaving quantumly. Right? We need a minimal, rock-solid test to verify three things at the exact same time: our single-qubit gates, our two-qubit entangling gates, and the measurement readout on the hardware itself. The Bell state sanity test beautifully solves this constraint by creating a simple state where two qubits should be perfectly correlated.
Now, when we execute that test, an exact simulator is going to show ideal correlations. You will literally only ever measure the qubits in the 0-0 state or the 1-1 state. But running it on real hardware reveals a completely different story. You'll see noise-distorted counts creeping into the 0-1 and 1-0 states. That discrepancy right there is exactly why quantum debugging requires strict statistical tracking and hardware awareness from day one.
Moving on to Section 2, basis rotation measurement patterns, or how we measure across axes.
Here's a fundamental quirk of quantum hardware. It natively measures only in the poly-Z basis. We can't just casually ask the computer for an X or Y measurement. Instead, we have to proactively trick the system by rotating our qubits right before measurement. We apply a Hadamard gate to measure X, or an S-Dagger-Hadamard combination to measure Y. This basis rotation pattern is an absolute must-have for chemistry and optimization algorithms where a Hamiltonian is expressed as a sum of different polystrings.
Next up, Section 3, parameterized onsets and expressivity, which deals with tuning QPU parameters.
So, what exactly is an ansatz? Well, it isn't just a static piece of code. Think of it as a highly dynamic trial state. We use rotation angles, represented by the Greek letter theta, alongside layers of entangling gates. And during execution, a classical optimizer actively updates these symbolic angles based on the measured expectation values that are coming back from the quantum hardware. The major takeaway here is that selecting an ansatz forces you into a pretty intense engineering balancing act. You're constantly weighing the mathematical expressivity of your model against the physical noise, the routing constraints, and the sheer measurement cost of the actual hardware.
Because if your onsets is too deep, the hardware noise will literally destroy your signal before you even get a measurement.
On to Section 4, the compute, use, uncompute pattern. This is all about memory reversibility.
Now, this specific pattern frequently trips up classical programmers. It unfolds in 3 distinct phases. In phase 1, we start by calculating a temporary arithmetic result or a reversible predicate. But, and here is the major catch with quantum systems, this action inherently entangles a temporary work register with the rest of the computation. They are now mathematically linked together.
Next, in phase 2, we actually put that temporary value to work. A classic example of this is kicking back a phase to our target qubits. This specific mechanic is completely foundational to massive algorithmic frameworks. It's the secret sauce behind the oracles in Grover search and the complex arithmetic driving Shor's algorithm.
Finally, and I can't stress this enough, this is a critical engineering requirement you simply cannot skip. We must hit phase 3 and uncompute those temporary values. Think of it like cleaning up a shared workspace after a messy project. You have to run the operations in reverse to clear out the temporary register. If you forget this step, the lingering garbage entanglement will completely wreck the quantum interference we rely on and corrupt your final measurement statistics.
Let's look at Section 5, Batch Execution and Observable Grouping, focusing on cloud optimization.
This part is all about efficiency. Because quantum processors are usually accessed over the cloud, sending one circuit at a time is painfully slow. To fix this, we group commuting Hamiltonian terms together and batch a ton of parameter settings into a single job. This dramatically reduces the number of distinct measurements required, and for complex chemistry or materials workloads, this optimization often makes or breaks the total runtime of your entire program.
And that distinction naturally leads us to the 2 foundational runtime primitives we use for these batches. You're going to use a sampler when you need raw distributions or bit string samples, say for testing or pure sampling tasks. But you switch over to an estimator when you need the average expectation values for your Hamiltonians, which is exactly what variational algorithms demand.
Finally, Section 6, the minimal VQE workflow, our hybrid architecture.
Putting all these pieces together proves that a modern quantum program is rarely just a simple script. It's a full-blown state preparation and measurement experiment. You build a Hamiltonian, choose that carefully balanced ansatz, use the estimator to get the energy, and then tightly loop back to a classical CPU to update the parameters using machine learning-style optimization. And of course, you validate against a baseline and report your statistical uncertainty at the very end.
Because quantum programming truly is a complex engineering stack of math, software, compilers, and strict hardware limits, it forces us to constantly reevaluate how we do things. As we rely on these many workflows today, it leaves us with a fascinating question. How will our current patterns scale, and which ones will completely break when error-corrected logical qubits finally arrive? It's a massive challenge, and honestly, an incredibly exciting frontier for the next generation of quantum software engineers.
Look, we really need to reframe how we talk about quantum programming. It's so tempting to just picture a quantum computer as this magic black box, right? You feed it a really complex problem, and boom, it magically spits out an exponentially faster answer. But that is just not the reality. Quantum programming is actually a rigorous, deeply layered engineering stack. It is this intense combination of heavy mathematics, strict physical hardware constraints, software compilation, and advanced statistics. And its foundational motivation isn't really to run your standard enterprise software faster. The real goal is to simulate nature itself, right down at the subatomic level.
Here's the roadmap for today's explainer. First, the quantum simulation imperative. Second, the quantum chemistry workflow. Third, we'll go inside the VQE algorithm. Fourth, near-term versus fault-tolerant systems. And finally, engineering materials and medicines.
Part 1. The quantum simulation imperative. Simulating quantum systems is the foundational motivation for all of this, and it really comes down to a problem of scale, a scale that completely overwhelms our classical machines. Think about it. When you simulate classical physics, adding a new particle basically just adds a few more coordinates to keep track of. No big deal. But quantum systems naturally live in this mathematical vector space called a Hilbert space. You can think of it like a rapidly expanding map of possibilities. If you have a system of n qubits, its state vector is defined by 2 to the nth power complex amplitudes. That means the size of your computational space is growing exponentially with every single particle you add. Because of that massive exponential scaling, classical computers literally just choke
when they try to simulate many-body quantum dynamics and complex molecular problems. But remember, this massive space isn't just a free source of exponential speedup. We still have to engineer the algorithm to force the right answers to interfere constructively just so we can actually measure them.
So how do we actually translate a real problem in nature into quantum code? Well, here is the high-level pipeline. Step 1 is defining your domain problem. Maybe it's a specific molecule or a complex magnetic material. Step 2 is formulating that exact problem as a Hamiltonian, which is essentially just a rigorous mathematical model of the system's total energy. And then step 3 is where the actual programming happens. You either map that Hamiltonian to a set of digital qubits using logic gates, or say you're using something like neutral atom hardware, you map it to an analog physical schedule where the parameters evolve over continuous time.
Part 2. The quantum chemistry workflow.
Let's dive into the quantum chemistry workflow and see how this all builds into a multi-layered sequence. Now, before a quantum computer is even touched, there is a massive classical pre-processing phase. Step 1 is defining the molecular geometry, so the literal physical arrangement of the atoms. Step 2 requires selecting a basis set to represent the quantum orbitals. Step 3 is using classical algorithms, like Hartree-Fock methods, to construct the electronic structure Hamiltonian. All of this heavy lifting, it happens on a classical CPU just to figure out what the quantum computer actually needs to solve.
Once we have that classical data, we've got to transform it into a quantum-native format. Step 1 here is constructing fermionic operators, which is essentially the mathematical language of electrons. But qubits aren't electrons, right? So step 2 requires these complex mathematical transformations to map those fermionic operators into qubit operators. Because qubit resources are incredibly scarce right now, step 3 involves selecting active spaces or symmetries to freeze out core electrons and artificially shrink the size of the problem. And finally, in step 4, you actually choose the algorithm that gets sent to the hardware. So the absolutely crucial point is this. The programming challenge is this entire pipeline. It is not just slapping a few gates together into a circuit and hitting run. A quantum programmer is out there actively managing the qubit mapping, carefully choosing the right parameterized circuit, or ansatz. They're strategically grouping commuting observables just to save runtime, explicitly allocating the number of measurement shots, constantly babysitting classical optimizer stability, and heavily layering on error mitigation. And most importantly, it requires strict validation against strong classical chemistry methods to ensure the quantum results aren't just noisy garbage. Honestly, you really have to think like an experimental scientist.
Part 3. Inside the VQE algorithm.
Speaking of experimental algorithms, let's look under the hood of the Variational Quantum Eigensolver, or VQE. This is basically the flagship algorithm for chemistry experiments right now. VQE is super attractive for near-term devices because today's hardware is frankly pretty noisy. The longer a circuit runs, the more the qubits decohere and lose their state. So VQE gets around this by using very shallow circuits just to prepare a state. Instead of running one massively long coherent computation, it relies on a ton of repeated measurements and it completely offloads the heavy mathematical optimization work to a classical computer.
Let's look at how this hybrid loop works in practice. Step 1. The quantum processing unit prepares a parameterized trial state, known as the ansatz. Step 2. The QPU acts purely as an estimator, measuring the Hamiltonian expectation value, which is essentially it taking a guess at the energy of that specific state. Step 3. That energy value gets passed straight over to a classical CPU, which uses an optimizer to tweak the parameters. Step 4. We check for energy convergence, and then this cycle just repeats, tweaking parameters, measuring, over and over, until the lowest energy ground state is eventually found.
But we really need to ground the hype right here, because VQE faces some severe engineering limitations in the real world. If you choose the wrong circuit, you get ansatz bias, meaning it physically cannot represent the correct chemistry no matter what you do. You can hit severe trainability problems like barren plateaus, where the classical optimizer just gets completely lost on a flat mathematical landscape, entirely unable to find the downhill slope to the right answer. Plus, there is massive measurement overhead because you need thousands of finite shots just to reduce this statistical uncertainty. When you combine all that optimizer instability with literal hardware noise, VQE becomes a deeply difficult statistical experiment to get right.
Part 4. Near-term versus fault-tolerant.
Let's zoom out for a second and contrast the experimental tools we are forced to use today with the rigorous fault-tolerant tools we're going to require for the future. On the one side, we have our near-term workflows. We just discussed VQE, along with short-depth time evolution and noisy sampling. They tolerate noise, sure, but they have very limited scalability. On the other side, we have our fault-tolerant workflows. These are the horizon targets: quantum phase estimation, qubitization, and quantum signal processing. Now, you don't program these by counting physical circuit depth. You program them using logical resource estimates. You have to meticulously track your T count, the number of non-Clifford gates you're using, because in the future, generating those specific gates is going to consume up to 90% of your hardware's entire error correction overhead.
Part 5. Engineering Materials and Medicines.
So what is the actual payoff for solving all these intense compilation and error correction problems? It is the macro-level goal of engineering entirely new materials and medicines. We're aiming to design topological and moire materials, things like supermoire twisted graphene to unlock totally novel superconducting properties. We are talking about mapping complex protein folding models and unraveling photosynthetic mechanisms so we can design better solar cells or entirely new pharmaceutical catalysts. And we have to be realistic here, classical benchmarking is constantly pushing the limits. Researchers recently used quantum-inspired tensor networks to simulate quasicrystals encompassing over 268 million computational sites. That is the massive, staggering scale of the benchmark that quantum computers will have to definitively beat.
The crucial takeaway to remember is this. Yes, chemistry and materials are absolutely the most promising applications precisely because they are naturally quantum systems, but making useful claims of quantum advantage? That requires incredibly careful domain modeling, strict resource accounting of every single logical gate and measurement shot, and ruthless, rigorous benchmarking against the absolute best classical baselines available. You simply can't just run a noisy circuit and declare that you've solved chemistry.
Which really leaves us with this final provocative question. If quantum advantage is measured not merely by executing a piece of code without crashing, but by rigorously proving you've beaten the absolute best classical benchmarks under strict statistical constraints, is your quantum simulation truly a conventional software application yet, or is it, for now, a highly precise physics experiment?
You know, programming a quantum computer is definitely not just one single monolithic task. It's actually a pretty complex stack of choices spanning different computation models, software abstractions, and hardware targets. In this explainer, we're breaking down the three major paradigms of quantum optimization: gate model workflows, quantum annealing, and analog Hamiltonian simulation. Our goal here? To cut right through the hype and establish a rigorous engineering framework for how these distinct architectures actually go about solving complex problems.
Here's the roadmap for this explainer. First, gate model QAOA workflows. 2. Evaluating optimization claims. 3. Quantum annealing and QUBO. 4. The central embedding problem. 5. Analog Hamiltonian simulation. And finally, number 6, contrasting evaluation metrics. Let's dive in.
Starting off with Section 1, Gate Model QAOA Workflows, which is really the discrete approach.
Okay, before we can even think about mapping a problem to quantum hardware, we have to lock in on the mathematical heart of the whole thing, the Hamiltonian. You can kind of think of a Hamiltonian as this vast topographical map of a system's total energy. So when we tackle a graph optimization problem, like MaxCut for example, we map it over to what's called a cost Hamiltonian. And the absolute crucial takeaway here? The deepest valley on that map, the lowest energy state, that corresponds exactly to the optimal classical solution we're hunting for.
So how exactly does QAOA find that deepest valley? Well, it runs this continuous hybrid loop. First up, the quantum circuit alternates between cost and mixer operations. Next, the quantum processing unit fires off repeated measurements. We call these shots, just to estimate the objective values. And then a classical optimizer steps in, it evaluates those results, tunes the angles, and updates the parameters for the next run. Honestly, it's just a relentless high-speed relay race between the QPU and the classical processor.
Now, right in the middle of all of this is the integer p. This is your circuit depth parameter. It dictates exactly how many times we alternate those cost and mixer operations. On paper, sure, cranking up p gives you a much sharper, more accurate approximation. But out in the wild, on noisy physical hardware, a higher p means a much deeper circuit. You're basically leaving your fragile quantum state exposed to way more decoherence and operational errors as that circuit gets deeper.
Because of that noise, QAOA is definitely not some plug-and-play magic bullet. Its performance relies on a pretty brutal reality check. I mean, a dense problem graph might look mathematically elegant, but if your hardware has sparse fixed connectivity, you'll be forced to insert a massive amount of routing gates just to make it fit. Throw in your parameter initialization strategy, the robustness of your classical optimizer, your total measurement budget, and that transpiled circuit depth, and you quickly realize something. If these aren't managed perfectly, hardware noise is literally going to drown out your optimization.
Moving on to Section 2, Evaluating Optimization Claims, or as I like to call it, the reality check.
All right, we really need to clear the air on a major misconception here. Successfully encoding and running some tiny toy optimization instance on a quantum computer, that's a fantastic scientific milestone, for sure, but it absolutely does not prove that a quantum heuristic beats an advanced classical solver. We have to remember that classical optimization is incredibly powerful, massively scalable, and getting better every single day.
So, if we want to separate actual quantum advantage from the PR hype, we have to demand really specific metrics. You need the approximation metric stacked up against the absolute best classical baseline, not just some deliberately weak one. You also need the total shot count and objective evaluations, right? That reveals the true execution overhead. We have to inspect the optimizer settings to make sure classical fine-tuning isn't secretly doing all the heavy lifting. We need the transpiled circuit depth to expose the real routing and native gate expansion costs. And finally, were these parameters trained on an idealized simulator or on noisy physical hardware? Because without these receipts, a successful run doesn't actually mean much for real-world competitiveness.
That brings us to Section 3, Quantum Annealing and QUBO, the energy landscape.
Now, we are looking at two starkly different paradigms here. Gate model workflows, which we just talked about, compute by firing discrete sequential instructions through a circuit. But adiabatic and annealing workflows, they completely rewrite those rules. You aren't compiling sequential circuits here at all. Instead, you encode your final answer into a low-energy state of a final Hamiltonian, and then you just let the physical system continuously evolve from a much easier initial state.
And because you aren't writing traditional circuits, your source code looks entirely different. The primary translation layer here is QUBO. That's quadratic unconstrained binary optimization. If you're working with commercial toolkits, say D-Wave Ocean, your entire job essentially becomes translating business logic into this very specific mathematical model. You are literally turning real-world, discrete optimization problems into a binary quadratic landscape.
All right, Section 4, the central embedding problem.
So, what's the ultimate bottleneck in an annealing workflow? It's this compiler challenge of embedding. You have to formulate your logical QUBO or Ising model and then physically map that problem graph onto fixed hardware topologies, like D-Wave's Zephyr graph, for instance. It's kind of like forcing a highly connected pegboard onto a sparse grid. To make it fit, you often have to set chain strengths, meaning you chain multiple physical qubits together just to represent one single logical variable. This minor embedding overhead can drastically inflate your costs, completely eating up your measurement budget and impacting sample quality before the calculation even gets going. You really have to lean on hybrid classical assistance and carefully inspect those sample energies. Next up is Section 5, Analog Hamiltonian Simulation, where physical geometry literally becomes your code. Honestly, this is where things get pretty wild. In digital circuits, your program is defined by abstract logic gates, your CNOTs, your Hadamards, things like that. But in analog Hamiltonian simulation, your program is defined by continuous, time-dependent, and space-dependent physical parameters. You are no longer feeding the machine abstract math. You are manipulating the literal physical evolution of the quantum system in real time.
A perfect example of this in action is a neutral atom array, like the ones you can access on Amazon Bracket. In these specific workflows, the physical position and geometry of the atoms literally is the program. Instead of gates, your software specifies laser detunings, amplitudes, and interaction schedules. You're basically playing 3D Tetris with individual atoms, arranging them in physical space so they perfectly mirror the exact structure of the optimization problem you're trying to solve. It absolutely requires incredibly geometry-aware problem embedding.
And finally, Section 6, Contrasting Evaluation Metrics.
When you look under the hood across all three of these architectures, you quickly realize that quantum engineers are obsessing over entirely different things. In the gate model, with QOA, it's all about circuit depth, 2-qubit gates, transpilation expansion, and observables. But over in quantum annealing, they're monitoring energy models, that brutal embedding overhead, sample quality, and hybrid solver behavior. And then in analog workflows, it's all about physical schedules, device-specific constraints, measured correlations, and the literal geometry of the atoms. They are all chasing solutions to the very same complex problems, but they are speaking completely different engineering languages.
Which leaves us with one final thought for this explainer. The next time you see a massive quantum optimization milestone hit the headlines, I want you to ask yourself, are we merely evaluating the raw, isolated physical potential of those qubits, or are we rigorously demanding to see the true efficiency of the entire hybrid engineering stack, the math, the compilers, the physical routing, and the classical optimizers combined? Because at the end of the day, the reality of quantum advantage lies in the whole stack. Let's get right into one of the most hyped and honestly most misunderstood concepts in tech today. If you just read the headlines, you think quantum machine learning or QML is some magical shortcut to AGI. Like it's a silver bullet that's going to make neural networks infinitely faster overnight. Well, we need to dismantle that hype right now. QML is not magic. Actually, it's a highly specialized hybrid engineering discipline. We're talking about a rigorous blend of quantum mechanics, software engineering, and classical statistics, all trying to figure out if quantum systems can give us specific representational or sample efficiency edges. And let me tell you, pulling that off means battling some truly brutal hardware constraints.
Here's how we're breaking it down today. First, we'll look at differentiable quantum programming. Second, the core QML patterns. Third, the obstacles and reality checks, because there are plenty. Fourth, we'll open up the advanced QML toolkit. And finally, number 5, we'll walk through a practical QML workflow.
All right, Section 1, differentiable quantum programming. Basically, how we map quantum concepts right onto classical ML architectures.
To really get QML, you absolutely have to understand the Q node. Think of a Q node as just a quantum circuit that's being treated as a differentiable node, or function, inside a much larger classical computational graph. It's kind of like a super specialized math coprocessor. Imagine an early GPU just handling very specific offloaded calculations. Frameworks like PennyLane are built totally around this exact idea. The big takeaway here, the quantum circuit is just one piece of a hybrid puzzle. The quantum processing unit, the QPU, runs the circuit and hands back samples or expectation values. From there, a classical autodiff framework, think PyTorch or TensorFlow, grabs those values, crunches the gradients, and updates the parameters. The quantum computer is definitely not running the whole show. It's just a specialized accelerator sitting inside a classical machine learning loop.
Let's build a quick translation bridge between the classical and quantum ML worlds. In classical ML, you're usually tweaking neural network weights, right? Well, in QML, those weights become trainable rotations and entangling layers inside your quantum circuit. A classical forward pass, that translates to preparing a quantum state and measuring observables. But check out that last row, the loss function. Notice how in QML, the loss function stays entirely classical. The classical computer is the one looking at the output, figuring out how wrong the quantum circuit was, and then using classical optimization frameworks to update those quantum parameters so it can try again.
Moving on to Section 2, the core QML patterns. Let's look at the architectural designs folks are actually testing out in the wild.
Right now, the field is playing around with a few major families of quantum models. We're seeing things like variational classifiers and quantum neural networks, alongside quantum kernels, generative or sampling-oriented circuits, and quantum chemistry optimization models. Now, they all have different names and they tackle different kinds of data, but here's the secret. They literally all rely on the exact same underlying mechanism. They are all using a classical optimizer to train a parameterized quantum circuit. And here is that shared mechanism in action. Whether you're firing up a quantum neural network or running a quantum chemistry simulation, you are almost always running some flavor of the VQE, the variational quantum eigensolver loop. It goes like this. Step 1, you prepare a parameterized quantum state. Step 2, measure an observable or a distribution. Step 3, compute a classical loss function. And step 4, use your classical optimizer to update the parameters and do it all over again. I really want this loop to stick in your mind. The classical CPU does all the heavy lifting, the optimization, the control logic, the batching. The QPU, it only evaluates the expectation. That's it.
All right, Section 3, obstacles and reality checks. Let's talk about the hardware constraints.
Okay, here's the catch. We really need a heavy dose of reality here, and it starts with data. In classical ML, loading data is basically a solved problem. You can shove gigabytes of data through a GPU in fractions of a second. But try doing that on a quantum machine, you are going to slam into severe gate and feature map overhead just trying to embed that classical data into a quantum state. It is a huge bottleneck. You literally have to mathematically map classical data points into quantum amplitudes or rotations, which means physically executing quantum gates. For big datasets, the circuit depth you need just to load the data usually wipes out any algorithmic speedup the quantum computer might have even given you.
And it gets tougher. When we tried training on today's noisy intermediate-scale quantum, or NISQ hardware, we hit some brutal physical walls. First up, barren plateaus, in large, unstructured circuit designs. Imagine you're trying to find the lowest point in a desert that is completely, perfectly flattened in every single direction. Your classical optimizer has literally no clue which way to step because the gradient landscape goes exponentially flat as the system gets bigger. Second,
Physical hardware noise is out there literally washing out your gradients. It buries the signal entirely in decoherence and errors. And third, just to get a clean estimate of that gradient, you're facing massive measurement costs. We're talking millions of repeated circuit executions or shots just to make one single parameter update.
Which brings us to a massive reality check that really summarizes where the industry is at right now. Quote, "The burden of proof is high because classical ML is powerful, scalable, and rapidly improving. QML code should be benchmarked against classical baselines, ablations, and noise-aware simulations." Unquote. The truth? Broad practical advantage for QML is still unproven. If you build a QML model, you can't just run it on some tiny toy dataset and declare victory. No way. You have to pit it head-to-head against state-of-the-art classical heuristics under super strict measurement budgets just to see if that quantum subroutine is actually pulling its weight.
That takes us to Section 4, the Advanced QML Toolkit. Let's dig into some compiler-level features.
As the QML ecosystem grows up, frameworks like PennyLane are bringing in some seriously sophisticated compiler features. Take Catalyst QDIT, for example. That's Quantum Just-in-Time Compilation. It's this powerful tool that dynamically compiles hybrid quantum classical control flows. It preserves your gradient workflows, which means researchers can rapidly prototype in Python while still getting the blazing execution speed of compiled binaries. But pay close attention to the framing here. This is a research-facing capability. It is not an automatic advantage for applications. It opens up new doors for what researchers can express and test, but it definitely doesn't magically fix the underlying hardware noise.
Beyond compilation, developers are also grabbing tools for poly-based computation, or PBC. This lets you test algorithms using poly measurements, which happens to be the native language of error-corrected, fault-tolerant surface codes. By baking in PBC, modern SDKs are letting researchers simulate and optimize their algorithms today for the fault-tolerant machines that are being built for tomorrow. But again, just to be crystal clear, this expands research capabilities. It is not a magical shortcut.
Finally, rounding out the toolkit, we have templates for structures like QRAM, Quantum Random Access Memory, and IQP-related constructs. Now, IQP circuits are notoriously hard to sample from classically, which makes them really interesting testbeds. These templates let developers easily drop these heavy-duty mathematical structures right into their workflows. But keeping with our reality check theme, these are advanced research tools meant to evaluate very specific circuit constructs. They are not turnkey solutions that are suddenly going to hand you quantum supremacy.
Let's bring it all together in Section 5, a practical QML workflow. Here is your hardened engineering blueprint.
If you're going to dive into QML responsibly today, you need a rigorous checklist. So here it is. Step 1. Carefully pick your data encoding strategy and your ansatz, your circuit architecture. Step 2. Run the whole thing on an exact simulator first, just to make sure the math actually works. Step 3. Benchmark it relentlessly against classical methods. Seriously, don't skip that. Step 4. Test how sensitive your model is to hardware noise by throwing it into a noisy simulator. Step 5 is absolutely critical. Inspect your compiled circuits. Your source code might look nice and shallow, but once a compiler routes it for a specific piece of hardware, the gate count can totally explode. You have to verify what's actually being sent to the machine. And finally, Step 6, report your shot budgets and uncertainty, and only scale up to physical hardware when the evidence actually supports it.
So it all boils down to this. Is a quantum subroutine truly the right tool for your problem? Anyone engineering in this space has to ask themselves this constantly. Quantum programming is an incredibly fascinating stack. It combines heavy math, compilers, tricky statistics, and strict hardware constraints. But let's be clear, it is not just a generic drop-in upgrade for classical code. It is an incredibly specialized accelerator. Approaching it with a rigorous engineering-first mindset, that is absolutely the only way we're going to separate the hype from true, scalable innovation.
Segment 15 of 20. Fault-tolerant algorithms, resource estimation, and long-range speedups. Look, when we talk about programming quantum computers, we are fundamentally dealing with a massive dichotomy. On one side, we've got the near-term reality, right? We're talking heuristic experiments running on noisy, highly constrained hardware. But then on the flip side, we have the rigorous, long-term ambition of fault-tolerant quantum algorithms. These are the legendary protocols that literally promise to reshape cryptography, chemistry, and computation itself. So, today, we're going to explore this divide and look at exactly how software engineers are bridging the gap between theoretical math and actual physical hardware.
Here's our roadmap for this segment. First, noisy versus fault-tolerant URAs. Second, the horizon algorithms. Third, resource estimation, which acts as our bridge. And finally, 4, the actionable horizon.
All right, let's jump right into Section 1, Noisy versus Fault-Tolerant Errors, a quantum reality check.
So, near-term noisy algorithms, think VQE or QoA, they're essentially hybrid quantum classical experiments. They manage to tolerate the noise of our current physical devices by using relatively shallow circuits, taking a bunch of repeated measurements, and then relying on a classical optimizer to actually find the answer. Now, contrast that with long-range fault-tolerant algorithms like Shor's or quantum phase estimation. These celebrated quantum speedups, they absolutely cannot survive the noise of today's machines. They demand incredibly deep, coherent circuits and resources that are just wildly beyond current routine hardware capabilities. They absolutely require quantum error correction and something called logical qubits.
Now, you might be wondering, what exactly is a logical qubit? Well, it's an encode qubit that is protected by many physical qubits and constant error correction measurements. Think of it like a computational fortress. Because individual physical qubits are super fragile and prone to errors from their environment, we literally have to weave a whole bunch of them together. We're constantly running error correction syndrome measurements to catch and fix mistakes on the fly without actually destroying the underlying quantum information. So the absolute crucial point here is this. Logical qubits are the absolute prerequisite for any long, complex quantum computation to actually survive.
Moving on to Section 2, the Horizon Algorithms, deconstructing the magic of quantum speedups.
Let's start with the big one, the most famous one. Shor's algorithm provides polynomial time quantum algorithms for integer factoring and discrete logarithms. Now, under ideal assumptions, this completely threatens RSA and elliptic curve cryptography. But, and this is a massive but, this threat only actually materializes once sufficiently capable, fault-tolerant machines exist in the real world. It's a theoretical powerhouse for sure, but it is definitely not something you can just boot up on today's hardware.
To really understand why that is, we need to look at the incredibly strict conditions required to run it practically at cryptographic scales. Shor's isn't just one simple operation. It requires massive overhead for reversible modular arithmetic. It totally relies on quantum phase estimation. It needs those ultra-stable logical qubits we just talked about. And it requires fault-tolerant gates just to prevent errors from cascading out of control. Because of these severe conditions, software teams today are absolutely not running real key-size Shor circuits. Instead, the actionable takeaway is to prepare for this future right now through post-quantum cryptography standards.
But keep in mind, the engineering math behind these requirements is changing incredibly fast. Just a few years ago, back in 2021, estimates suggested we might need somewhere around 20 million noisy physical qubits to factor RSA 2048. Fast forward to 2025, and specific architectural advancements, things like high-efficiency quantum low-density parity check codes and brand-new hardware topologies, have actually brought that estimate down to under 1 million physical qubits, which could complete the task in under a week. While that is still a massive engineering hurdle, this drastic shift in resource estimates brings the theoretical threat so much closer to a realistic engineering timeline.
Now, Shor's isn't the only Horizon algorithm out there. Take Grover Search, for example. It promises a quadratic query speedup, but it strictly requires an efficient, reversible oracle and incredibly long coherent circuit depth. In fact, often, the oracle itself completely dominates the computational cost. Then there's amplitude estimation, which promises to surpass classical Monte Carlo techniques, but it relies heavily on ideal assumptions for probability estimation. Hamiltonian simulation offers incredible promise for things like chemistry and material science, but again, requires vast coherent resources to accurately model this quantum dynamics. And HHL for linear algebra, it promises exponential or polynomial speedups, but it actually demands sparse, well-conditioned matrices, super efficient state preparation, and it only extracts limited observables. It does not just magically print out the full solution vector for you. So, as you can see, the gap between theoretical promise and practical deployability is vast.
Let's look at Section 3, Resource Estimation, the Bridge, connecting abstract algorithms to hardware roadmaps.
Modern tools like the Azure Quantum Resource Estimator don't just guess at what we need, they calculate hardware requirements using a really rigorous four-step input process. First off, they take your application model. That's the actual algorithm source code or intermediate representation. Second, they map that against a physical architecture model, which accounts for real-world gate times and physical error rates. Third, they apply a quantum error correction and distillation model. And finally, they measure all of this against your overall error budget. This entire process determines if your algorithm is actually physically plausible to run in the real world. When we step into this fault-tolerant era, our whole vocabulary has to fundamentally change. We stop obsessing over just physical circuit depth, and we start optimizing for an entirely new set of metrics. T-count and T-depth, for instance, measure the absolute most expensive non-Clifford operations in your circuit. Then you have magic state distillation and T-factories. These are literally dedicated hardware zones that produce the resources for those T-gates. We have to meticulously track logical error rates versus physical error rates. We have to ensure our classical decoder latency can actually keep up with the quantum processor. And we have to calculate the specific code distance needed to protect the data. These metrics right here, these are the true currency of long-range quantum computing.
And I want to point out a staggering reality check regarding those resources. When you look at the physical footprint of a fault-tolerant algorithm, you might logically think most of the hardware is dedicated to running your core logic, right? Not even close. Often upwards of 90% of your physical resources are dedicated strictly to producing magic states via T-factories. Think about that. The actual algorithmic operations represent just a tiny, tiny slice of the pie. The sheer overhead of error correction and distillation is just massive.
Because of this massive overhead, resource estimators generate what we call a Pareto frontier. Basically, this illustrates the inherent trade-off developers are going to face between runtime, which is how fast the algorithm finishes, and physical qubits, which is the literal hardware footprint needed for the encoding and error correction. It's like a giant seesaw. You can design an architecture to run faster, absolutely, but it's going to require significantly more physical qubits to parallelize that error correction. Or you can save on physical qubits, but then your runtime is going to stretch out drastically. You constantly have to balance this scale.
This brings us to Section 4. The Actionable Horizon, Engineering for the Fault-Tolerant Era.
This transition to fault-tolerant programming radically shifts what we are actually trying to optimize for. Under the near-term paradigm, engineers spend their days optimizing shallow physical circuits, trying to brilliantly route around bad physical qubits, and using statistical methods just to mitigate noise. But in the fault-tolerant paradigm, the hardware noise is completely hidden beneath that error correction layer. So the software engineer's job completely shifts to optimizing logical resources, streamlining those massive magic state factories, and integrating highly efficient application-level decoders. It's a whole new ballgame.
So what are the actionable steps for software teams right now, today? Well, first, don't just sit around waiting for Shor's algorithm to run. You need to prepare your security infrastructure via post-quantum cryptography standards right now. Second, continuously monitor fault-tolerant resource estimates, because as we saw earlier, those timelines can shrink drastically when architectural breakthroughs happen. And third, treat quantum programming not as some theoretical physics project, but as a full end-to-end engineering stack. You absolutely have to bridge high-level math, advanced compilers, rigid hardware constraints, and complex cloud workflows all together.
Which leaves us here. I want to leave you with this provocative question to critically reflect on. As we leave the era of noisy, small-scale experiments and enter the regime of massive, fault-tolerant execution, will your algorithms survive the transition to logical resources, or will they break under the weight of their own overhead? Understanding the bridge of resource estimation is the only way you're going to find out.
To unlock the true potential of quantum computing, running those long-horizon algorithms like large-scale factorization or precise molecular chemistry, we've got to confront a pretty brutal reality right out of the gate. Current quantum hardware is noisy, and those errors compound incredibly quickly. So to make deep computations possible in principle, we absolutely must rely on a core mechanism, and that's quantum error correction. In this explainer, we're going to cover NISQ versus fault tolerance, physical versus logical qubits, error correction mechanics, the QEC runtime substrate, real-time classical control, and finally, the quantum engineering stack.
All right, let's dive straight into Section 1, NISQ versus fault tolerance.
Building long quantum computations requires a completely different engineering mindset than what we're used to today. Right now, a near-term or NISQ developer is constantly sweating over things like, is my physical circuit shallow enough to finish before the qubits decohere? Are my error mitigation assumptions actually acceptable? But a fault-tolerant developer? They live in an entirely different world. They're asking fundamentally different questions, like what's the required code distance to ensure safety? How many physical qubits are being consumed for logical operation? How many T-factories do I need just to generate complex quantum dates? And ultimately, what is the total error budget I'm allowed to spend? Logical programming fundamentally changes the very questions developers have to ask.
The absolutely crucial point here is this.
Quantum error correction is not just better error mitigation. It's a completely different execution regime. Error mitigation uses classical post-processing to slightly tidy up noisy results. But error correction, that is a massive paradigm shift. It fundamentally alters how the hardware and software interact with each other in real time.
Moving on to Section 2, we need to look at physical versus logical qubits.
Let's start with the physical qubit. Think of this as the bare, noisy, and incredibly fragile hardware unit. It doesn't matter if we're talking about a superconducting loop or a trapped ion. It is heavily susceptible to environmental decoherence and operational errors. That fragility is exactly why deep, complex algorithms just flat out fail on today's machines. The information simply degrades way before the computation is even finished.
And that brings us to the logical qubit. This is the protected quantum information. But here's the catch. It isn't just sitting on one fragile piece of hardware. Instead, it's encoded across a lattice, or a code block, of many physical qubits all working together. You see, scalable computation requires spreading one single piece of logical information across a vast array of physical hardware units. That way, if one physical qubit fails, the logical information still survives.
So let's be real for a second. Strict, no-hype reality. A logical qubit is not just a slightly upgraded physical component you can easily manufacture. It's a highly expensive, rigorously engineered system. Running something like Shor's algorithm requires a massive ratio of physical qubits dedicated entirely to protecting the logical information. We are literally talking about hundreds, maybe even thousands of physical qubits just to yield one stable logical qubit.
That brings us to Section 3, Error Correction Mechanics.
The big problem in quantum mechanics is that measuring a state collapses it, right? So how do you check for errors without destroying the very data you're trying to protect? Well, you extract an error syndrome. This is an incredibly clever workaround that gathers indirect information about the error. It allows you to detect anomalies without ever directly measuring the protected logical quantum state itself.
To actually extract those syndromes, we use what are called stabilizers. These are active, carefully designed operations that are repeatedly measured. They constantly ping the physical qubit lattice, checking for errors, safely pulling out the error syndromes, and immediately feeding them to a classical decoder. You can think of that decoder almost like an air traffic controller, constantly tracking exactly where the faults are popping up.
So what are the core engineering concepts here? We've got surface codes, which are fantastic for 2D nearest neighbor layouts, and advanced QLDPC codes, which require architectures with long-range connectivity, kind of like IBM's experimental quantum loon. We've also got magic state distillation, T-gates, and T-factories. And what is truly staggering here is the resource drain. Algorithms often dedicate upwards of 90% of the machine's total physical resources just to these factories, constantly distilling magic states to allow complex, non-Clifford operations to occur reliably. Those are the advanced mathematical steps needed for true quantum advantage.
Let's look at how this runs in practice with Section 4, the QEC runtime substrate.
Shifting focus to this software execution loop running beneath your high-level program, we find that the QEC runtime substrate is not some static program. It's a rapid-fire operational loop managed by classical systems. Step 1 is syndrome extraction. Step 2 is classical decoding to figure out what just went wrong. Step 3 is correction tracking, which is often just updating a software frame rather than physically flipping a qubit back. And Step 4 is executing the logical operations. This loop has to fire continuously, incredibly fast, just to keep the logical qubit alive.
Which leads perfectly into Section 5, real-time classical control.
Executing that super-fast, continuous loop directly dictates the architecture of the quantum hardware roadmaps we're seeing today. Hardware vendors are rushing to build specific features precisely because fault tolerance demands them. Faster measurement and reset, explicitly required for those continuous syndrome extraction loops. Reliable mid-circuit logic is completely necessary for dynamic circuits and qubit reuse. Long-range couplers are essential if we want to run highly efficient QLDPC codes. And neutral atom flexibility, like what AWS Bracket is exploring with Quera, is pursued because it allows for transversal logical connectivity, which drastically reduces the overhead needed.
Finally, let's pull all of this together in Section 6, the quantum engineering stack.
Let's step back and visualize the whole system required to orchestrate this. Quantum programming is absolutely no longer just writing a sequence of theoretical gates. It is a massive, incredibly complex engineering stack. You start way up at the high-level algorithm, lower it into a logical circuit, pass it through a fault-tolerant compiler, which then maps it onto an error correction code.
Below that, you've got the syndrome extraction protocols, the classical decoder tracking faults in real time, the analog physical control systems, and finally, the actual hardware substrate itself. It's an integration of math, software, compilers, statistics, and some intense hardware constraints.
But behind all of this complexity is the human element. To put things into perspective, we're looking at a massive projected increase of 550% in quantum technology jobs in regions like the Midwest by the 2030s. The industry desperately needs people who can actually navigate this deeply layered stack.
So, this leaves us with one incredibly crucial question. As quantum programming definitively transitions out of theoretical physics and into rigorous software engineering, who is actually going to build this massive fault-tolerant stack? The future really belongs to a deeply specialized, location-agnostic quantum workforce, software engineers who are ready to tame this incredible complexity and finally make scalable quantum computation a reality.
Okay, so if you look at the absolute central engineering constraint that's shaping literally all of quantum programming right now, it all comes down to one inescapable reality: hardware noise. We're just not in an era yet where you can write perfectly deterministic code, hit compile, and expect the hardware to run it flawlessly. Current quantum processors, they're noisy, they're finite, and man, they are incredibly sensitive to their environments. So modern quantum programming isn't just about the math and the logic anymore, it's fundamentally about how we manage, suppress, and mitigate all that noise.
All right, let's dive right into this. We're looking at the experimentalist journey today, starting with the NISQ reality, moving through error suppression and mitigation, looking at those trade-offs, and then wrapping up with statistical discipline and evidence management.
First up, Section 1, the NISQ reality, the hardware constraint shaping all quantum code.
So, before we even think about writing a single line of code, we've got to understand the hardware we're dealing with. Right now, we operate in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. What does that actually mean for us? Well, it means we have devices that are big enough to do some fascinating stuff, sure, but they are absolutely not error-corrected. Qubits decohere. They literally lose their state over time. The operations or gates we apply? Imperfect. Even the act of measuring introduces error. And here's the kicker. These errors accumulate with every step of your circuit depth. Hardware noise isn't just some pesky edge case we can ignore. It is our absolute first-class constraint.
And because these errors compound with every single extra operation, this noise dictates our decisions at literally every layer of the stack. First off, it strictly limits your ansatz design and your circuit depth. Then, it forces you into some really complex qubit routing and connectivity mapping. Think about it. If two qubits aren't physically connected on the chip, the compiler has to step in and insert swap gates to move that information around. That immediately spikes your 2-qubit gate count, which is a massive issue since those specific gates are the biggest source of operational errors. Finally, noise forces our hand on shot allocation, how we group observables, and makes us heavily reliant on classical post-processing. Your code is, quite literally, shaped by the raw physics of the chip.
Moving on to Section 2, error suppression, and how we actually prevent noise.
You can kind of think of error suppression as building this preventative shield before your experiment even begins. We're talking about preventative actions taken to reduce errors at the physical or control level, either right before or dynamically during circuit execution. This is pure prevention, plain and simple. It mostly happens on the compiler and hardware side of things, where the goal is just trying to ensure the physical operations run as cleanly as physically possible.
So how does the shield actually work in practice? Well, a massive chunk of suppression comes down to noise-aware compilation. That means deliberately rewriting your circuit to use the absolute quietest qubits on that specific chip. We're also using strategic routing to dodge bad connections and opting for shorter circuit depth scheduling so we can finish the calculation before decoherence just completely wrecks our data. Down at the lowest levels, engineers are applying things like pulse-aware control and dynamical decoupling. That's basically flipping qubits at really specific intervals to cancel out background noise. And why should you care? Because as an application developer, you are actively toggling these exact features when you select your transpilation optimization levels in frameworks like Qiskit or T-Kit.
All right, Section 3, error mitigation, or cleaning up our data.
Now, what's really interesting here is what happens when our preventative shield just isn't enough. We need to draw a really clear conceptual line. On one side, we have error suppression. That's our physical, compiler-based prevention. On the other side, we have error mitigation, which is all about classical inference and post-processing. They work together, sure, but they are totally distinct phases of your quantum pipeline.
So let's define that second part. Error mitigation is classical or experimental post-processing. The whole goal is to infer a better, cleaner estimate from your inherently messy, noisy results. But I really want to stress a crucial distinction here. It does this without fully protecting logical qubits. It is an inference filter. It's applied on your classical laptop or cloud server after the quantum device is totally finished running. There's no magic happening here. It's just pure statistics.
And here are some of the most common mitigation techniques you're going to see out in the wild today. Calibration readout errors. That adjusts your final measurements based on known biases in the hardware. Then there's zero-noise extrapolation, which is pretty clever. It intentionally amplifies the noise in the circuit so we can mathematically model it and then just subtract it out. We've also got probabilistic error cancellation verifying symmetries, where you basically throw out any results that violate the known physical laws of your specific problem, and combining multiple noisy estimates. Whenever you read a paper on a near-term quantum algorithm today, you kind of just have to assume that some combination of these techniques is running in the background to make those results legible.
Which brings us to Section 4, Mitigation Trade-offs and Costs.
Okay, time for a bit of an anti-hype reality check, because this perfectly illustrates the catch. These data cleaning techniques, they do not come for free. The costs you pay for that clearer data are steep and unavoidable. Look at the raw data. Your estimate accuracy is lower, yes, but your statistical variance and sampling costs sit at a nice, predictable base level. Now switch over to the mitigated data. Sure, your estimate accuracy improves, but the penalty is heavy. Your statistical variance gets amplified, meaning the spread of your data gets way wider. And to compensate for that, your sampling cost, the sheer number of shots you have to run on the hardware, multiplies dramatically.
And let's just state this firmly for the record. Error mitigation is not the same thing as fault-tolerant quantum error correction. Not even close. Mitigation completely relies on assumptions about the noise model, and honestly, it scales terribly. You simply cannot mitigate your way to a trillion-gate algorithm like Shor's. True fault tolerance requires massive physical overhead to build fully protected logical qubits. Mitigation is just a temporary bridge for the near term.
Let's move to Section 5, Statistical Discipline in Quantum.
So, because we are heavily relying on this noisy data and classical inference, you as a developer really have to adopt a strictly disciplined mindset. And the absolutely crucial point boils down to this number: 1. A single run of a quantum circuit gives you exactly one sample. Just one. It is not a definitive, deterministic answer like you'd get from a standard classical CPU.
Quantum programming is inherently statistical. Because so many of our workflows are just trying to estimate expectation values rather than magically finding a single correct bit string, our data is distributed. Just look at how these values behave. On the left, you've got your expected theoretical mean, the perfect world scenario. In the middle, your noisy raw mean gets dragged way down, skewed heavily by hardware decoherence. Then on the right, the mitigated estimated mean tries its best to push that value back toward the theoretical ideal. But as we just talked about, it comes with a significantly wider variance. This right here is exactly why you have to treat your output as an experimental distribution.
Because of all that, serious results absolutely require strict statistical guardrails. You have got to establish strict shot budgets. You need to know exactly how many times you must sample that device to overcome the variance. You have to meticulously calculate expectation values and constantly track your confidence intervals and standard errors. Without error bars, your data means basically nothing. Crucially, you need to compare those raw counts directly against the mitigated values. You want to make sure your technique didn't just invent a good answer, right? And you have to test how sensitive your results are to the mitigation assumptions themselves. Doing this is what actually differentiates true algorithmic behavior from just random finite shot fluctuations.
Finally, Section 6, the Evidence Management Rule. This leads us to what I consider the golden rule for any developer writing quantum programs on actual hardware today. If you're going to claim that your program works, you must transparently manage all of this evidence. Here's your checklist. Step 1, report both your raw results and your mitigated results. Step 2, explicitly document the uncertainty amplification and whatever method settings you used. Step 3, list out your circuit metrics and the backend metadata. Things like calibration drift matter immensely, because the exact same quantum chip is going to perform differently from a Tuesday to a Wednesday. And step 4, always provide exact simulator baselines and aggressive classical comparisons.
Ultimately, the whole mindset boils down to this.
Treat error handling as evidence management, not some magic correctness layer. The hardware is going to fight you, the transpiler is going to stretch out your circuit, the mitigation techniques are going to amplify your variance. You aren't just writing code anymore. You are building an evidentiary case that your quantum signal actually survived the noise.
And I'm going to leave you with this final thought to chew on. If your entire quantum program relies on perfectly guessing the underlying noise model just to mitigate your data into something usable, are you actually proving quantum advantage? Or are you just demonstrating classical overfitting? It is a really fine line in the NISQ era, and for sure, the only way to stay on the right side of it is through incredibly rigorous statistical discipline.
In segment 18 of 20 of our explainer, we're jumping right into how we actually rigorously test, debug, simulate, and report reproducible quantum software. Today, we're stripping away the hype and grounding quantum programming firmly in engineering reality. Look, quantum programming isn't just writing a faster version of some ordinary classical program, not even close. It's a highly specialized engineering stack where you have to combine advanced math, software design, compilers, physical hardware constraints, statistical analysis, and cloud workflows all into one.
Okay, let's dive into this roadmap. Here's the highly structured engineering stack we're covering today. First, we'll tackle the debugging problem. Then, choosing simulators. Third, the testing ladder. Fourth, we'll look at common programming bugs. Fifth, reproducible architecture. And finally, the essential metrics you absolutely need for serious reporting.
Part 1. The debugging problem.
Let's kick things off with the absolute core constraint of quantum software development: why standard classical software debugging simply fails when you apply it to quantum systems. Think about how ridiculously convenient classical debugging is. You can pause execution whenever you want with a breakpoint, copy the memory, print out deterministic variables, and inspect exactly what your program is up to, right? Well, quantum debugging strips every single one of those conveniences away. In quantum systems, your output is inherently probabilistic. But the biggest hurdle, the real deal breaker, is that a quantum state literally collapses upon measurement. You could think of it like Schrodinger's bug. The very moment you look at it, it changes. You simply cannot freely inspect an intermediate quantum state without permanently changing the trajectory of your entire computation.
And here's the thing, this isn't just some annoying hardware glitch, it's a fundamental law of physics known as the no-cloning theorem. This theorem states that it's physically impossible to create an independent and identical copy of an arbitrary unknown quantum state. So this completely blocks those simple snapshot and copy debugging methods we lean on so heavily in classical programming. Because you can't just snapshot the memory mid-execution, quantum developers have to act a lot more like experimental physicists. We have to rely on indirect methods. Things like simulators, exact invariance, histograms, statistical assertions, compiler inspection, and reproducible experiment records.
Moving on to part 2, choosing simulators.
Because we can't observe quantum states freely on actual hardware without destroying them, simulators become our absolute best friends. They're our primary substitute for direct observation. And the golden rule here? Local simulation usually comes before hardware execution. Let me be clear, running untested code on real noisy quantum hardware is slow, it's expensive, and it is a fast track to a complete engineering failure.
Now, what's really interesting about this is that exact simulation scales exponentially, meaning you will quickly run out of memory. So you have to choose your simulator wisely, based on the exact task at hand. For small circuits, you'll use a state vector simulator for exact pure state evolution. But when you need to test noise channels and error mitigation strategies, you need to shift gears to a density matrix or a noisy shot-based simulator. What if you're dealing with Clifford-heavy circuits? A stabilizer simulator is going to give you highly efficient testing. For highly structured, larger circuits that have limited entanglement, tensor network methods are incredibly powerful. If your work happens to involve analog schedules or annealing models, you'll want to deploy local analog simulators, right alongside exact and classical samplers. And finally, for fault-tolerant planning, like estimating logical qubits or T-counts, resource estimators are absolutely essential. Picking the right simulator at the right time before you ever touch a QPU is a fundamental quantum engineering skill.
All right, part 3. The testing ladder.
Let's see how this testing methodology builds. Quantum testing has to be a sequential, 6-step ladder, and skipping a rung almost guarantees you're going to miss a critical error. Step 1. Start with tiny exact cases, followed by Bell state and basis rotation sanity tests to verify basic entanglement. Step 2. Move up to checking exact invariance for oracles, reversible arithmetic, and uncomputation. Step 3. Introduce randomized or property-based checks, like verifying normalization. Step 4, and this is absolutely crucial,
Run transpilation equivalence checks. You have to verify that the compiler hasn't quietly altered your core logic when mapping to a specific hardware topology. Step 5. Execute noisy simulations to test how your program handles hardware approximations and statistical behavior. And finally, Step 6. Perform limited hardware runs, making sure you capture comprehensive metadata and statistical error bars.
Part 4. Common programming bugs.
So, the crucial point is that knowing your testing ladder is really only half the battle. You also need to know exactly what can go wrong. Consider this your mental checklist for the 7 most common pitfalls developers face. Number 1. Confusing amplitude with probability. Remember, amplitudes are complex numbers. You only get probabilities after taking their squared magnitudes. 2. Measuring too early. Accidental mid-circuit measurement can instantly turn your quantum algorithm into a purely classical randomized procedure. 3. Forgetting to uncompute. 4. Trusting pre-transpilation depth. 5. Ignoring shot noise. 6. Overfitting to a simulator. Listen, a circuit that works flawlessly in an exact simulator is very often going to fail on real hardware because of decoherence and routing overhead. And 7. Making unsupported advantage claims. Just because a quantum program ran successfully doesn't prove advantage unless you've rigorously compared it against the absolute best classical baselines.
Actually, let's zoom in on the third bug on that list for a second, because it's a massive and often totally invisible source of failure: forgetting to uncompute. Uncomputation is the process of applying inverse operations to clear out your temporary work registers. A lot of quantum programs compute a temporary value just to change a phase. Well, if you don't clean up that temporary register, it remains entangled with your output. And that garbage entanglement, it will completely corrupt your quantum interference.
Another massive trap is ignoring shot noise. Because quantum measurement is probabilistic by nature, a finite number of circuit executions, what we call shots, only gives you an estimator with sampling uncertainty. That statistical fluctuation is your shot noise. If you ignore it, you are going to gain a really dangerous, false overconfidence in your data. This is especially problematic in variational algorithms, where your classical optimizer might start making updates based entirely on finite shot statistical noise instead of actual algorithmic improvement.
Part 5. Reproducible architecture.
To really protect against all these experimental uncertainties, we need to zoom out from the specific bugs and look at the overall project architecture. Take a look at this quote: "Quantum programming is reproducible experimental computing, not only source code development." Writing quantum code demands the exact same rigorous mindset as being a numerical scientist or a hardware experimentalist. And this brilliantly illustrates how we structure that discipline. We use a 5-layer quantum architecture. At the top, the problem layer defines your domain models, like a Hamiltonian or graph, completely independent of any specific backend. Below that, the quantum model layer is where you actually build your parametrized circuits and observables. Then the compilation layer stores your transpiled circuits and optimization settings. Note this, you have to save the executed circuit here, not just the source code. Next, the execution layer handles the actual hardware or simulator submission, managing the batching, experiment configs, and your raw results. Finally, the analysis layer takes care of all your reports, tests, error mitigation, plotting, and statistical analysis. By strictly separating your problem logic from your backend logic, you preserve all the vital evidence you're going to need for later comparison.
Finally, Part 6. Essential metrics. To wrap things up, here are the exact metrics you need to produce a serious, rigorous quantum program report. You really need to separate algorithmic metrics from hardware constraints. On the algorithmic side, you must track logical and physical qubits, total gate counts, especially those 2-qubit gates, circuit depth, scheduled execution time, observables, polygroups, and your simulator and classical baselines. Over on the hardware and execution side, you need to document the calibration record, the SDK version, backend, layout, and coupling map. You absolutely must report raw counts, raw values, and mitigated values, complete with their error bars. Finally, record your shots, basis gates, optimizer settings, random seeds, environment lock files, and analysis scripts. Honestly, providing this level of exhaustive data is the only real way to prove computational advantage without relying on hype.
So, I'll leave you with this. Are you just writing quantum code, or are you engineering a rigorously reproducible quantum experiment? Because in this field, adopting a highly scientific, hardware-aware mindset isn't just a nice best practice. It is the fundamental requirement for success. Let's jump right into the actual rigorous engineering reality of where quantum programming is being applied today.
We're going to strip away the hype, the buzzwords, and look at the real stack. We hear so much about the promise of quantum computing, but in this explainer, we're strictly grounding that promise in hard engineering. Because here's the crucial point. Quantum applications, they aren't magic. They're precise state preparation and measurement experiments, and they carry a massive amount of classical overhead. A quantum program isn't just a magically faster version of a normal app. It's a highly specialized computational kernel, basically a circuit, wrapped up in a heavy classical framework that manages optimization, data preparation, compilation, and post-processing.
To unpack all of this, we have a really solid agenda. We'll methodically dissect these applications across 1. Chemistry and material simulation, 2. Optimization, logistics, and finance, 3. Cybersecurity and cryptography, 4. Scientific sampling and physics, and finally 5. Evaluating advantage claims.
All right, let's start with Section 1, Chemistry and Material Simulation, where we map subatomic interactions right to quantum circuits.
Now, this is arguably the most natural fit for quantum programming, and the sheer variety of workloads here brilliantly illustrates the breadth of industrial use cases being explored. We're talking about everything from discovering new therapeutic catalysts and modeling complex proteins to analyzing topological quasicrystals. The sources even highlight cutting-edge exploration like twisting van der Waals layers to engineer supermoire materials, all in the hunt for dissipationless electronics. It's pretty wild.
But what's truly fascinating is the actual engineering pipeline required to run these near-term experiments. You don't just hit a button and solve the chemistry problem. You have to construct the Hamiltonian, map those fermionic operators over to your qubits, execute a variational quantum eigensolver, apply error mitigation, and then let a classical optimizer update the parameters. It's a very tight, highly iterative hybrid loop.
However, if developers want to move beyond those near-term heuristics like VQE and truly scale up, they have to focus heavily on fault-tolerant targets. This means shifting your brain away from just looking at physical circuit depth on noisy qubits. Instead, you're focusing on logical resources, resource estimation, and phase estimation precision.
Moving on to Section 2, Optimization, Logistics, and Finance. This is all about navigating massive combinatorial problem spaces.
In this space, we're aggressively exploring use cases ranging from complex routing and inventory management all the way to financial portfolio analysis and volatility stress testing. The big question here is whether quantum systems can find better approximations in these highly constrained search spaces using methods like the quantum approximate optimization algorithm or quantum annealing.
But we've got to have a reality check here. Based on the sources, a broad production-ready advantage in optimization is totally unresolved right now. Quantum methods like QAOA and annealing have to go head-to-head with incredibly mature classical baselines. Advanced classical heuristics and optimized Monte Carlo methods are already lightning-fast and extremely cheap to run. So the absolutely crucial takeaway here is that a successful optimization run on quantum hardware only proves that a small problem instance can be mathematically encoded. That's it. It doesn't automatically prove it can overcome heavy physical overheads to actually beat classical solvers. To seriously evaluate these claims, you have to fully account for the costs of data loading, your measurement budgets, routing compilation, and hardware noise.
Let's shift gears to Section 3, Cybersecurity and Cryptography, specifically post-quantum migration and fault-tolerant horizons. Here, the conversation shifts from near-term heuristics to long-term threats.
We know Shor's algorithm provides polynomial time solutions for integer factoring, which is a massive threat to RSA and elliptic curve cryptography. But since Shor's requires massive, error-corrected, fault-tolerant machines that literally don't exist yet, the immediate threat we're looking at is known as harvest now, decrypt later. Basically, this is the risk that encrypted data stolen today is just archived by adversaries who are patiently waiting for the day a sufficiently capable quantum computer is finally turned on.
And that specific risk is exactly why organizations are migrating to post-quantum cryptography right now. It's absolutely vital to distinguish between the highly practical, real-world security work of deploying quantum-resistant classical standards today versus the future reality of actually programming and executing quantum attacks.
Up next is Section 4, Scientific Sampling and Physics. We're probing the edges of quantum ergodicity here. And this is where early, verifiable demonstrations of quantum utility are actually starting to emerge.
The general consensus in the field right now is that early, genuinely useful programs are going to look a whole lot more like carefully designed physics experiments than your everyday enterprise app. As we've seen with things like Google's Quantum Echoes announcement, near-term advantage is tied strictly to highly structured, verifiable protocols. We are definitely not talking about arbitrary software acceleration for enterprise IT, we're talking about precision physics.
These scientific sampling tasks generate immense value by exploring phenomena that are incredibly hard to simulate classically. They're probing quantum dynamics, understanding chaos, observing thermalization, and measuring complex correlations. But because the space is so complex, it demands strict verification structures, and it constantly has to be compared against the absolute best classical simulation methods available.
Finally, we arrive at Section 5, Evaluating Advantage Claims, or as I like to call it, the Evidence Discipline Checklist.
If you're going to assess quantum claims, you absolutely need a rigorous framework. First up, look at algorithmic integrity and hardware feasibility. Ask yourself, does this problem genuinely map to quantum mechanics, or is the data loading overhead going to completely wipe out any possible speedup? And on the physical side, does the compiled circuit actually fit the target hardware? Is the required shot cost even acceptable before the machine decoheres?
You also have to demand statistical rigor. Any serious claim has to report its error mitigation uncertainty. Seriously, show us the error bars. And, perhaps most importantly, did this quantum experiment fairly beat the absolute best classical alternative out there, with every single overhead fully accounted for?
Grasping this entire landscape means you have to treat quantum computing as a deeply integrated stack. It's a strict combination of math, software, compiler constraints, statistical realities, and cloud workflows. The compiler and the statistics dictate the success of the program just as much as the quantum hardware itself.
So keep this baseline anchor in mind. The next time you see a massive breakthrough claim in the news, whether it's about a new catalyst or a crazy fast financial routing algorithm, ask yourself, does it truly survive rigorous engineering scrutiny? Does the next quantum headline you read actually pass the evidence discipline checklist?
All right, let's jump right into this capstone explainer. Today, we've got a very specific dual purpose. We are laying out a rigorous, actionable roadmap for entering the quantum workforce, and we're delivering a master recap of the entire 20-segment quantum engineering stack that we've been exploring in our source materials. If you're looking to move from just theoretical interest to actually engineering quantum software, well, this is your blueprint.
Here's our roadmap for today. We're going to cover 1. Prerequisites and fundamentals. 2. The 6-stage learner workflow. 3. Education and community ecosystem. 4. The quantum programming stack. 5. Essential developer habits. And finally, number 6, the realistic quantum future.
First up, Section 1, Prerequisites and Fundamentals. This is really the groundwork for quantum engineering.
You'll probably notice right away just how heavily these prerequisites skew toward math over traditional computer science. And that's because quantum programming isn't just writing a faster classical function, right? It is fundamentally a state preparation and measurement experiment. To manipulate a qubit, which is described by a normalized vector with complex amplitudes, you absolutely need linear algebra, complex numbers, and probability. You have to understand how tensor products build multi-qubit states, how unitary matrices act as gates, and how entanglement works. Honestly, if you don't have this mathematical baseline, the code simply won't make sense.
But once you've got that math down, you've got to get hands-on with simulation. This means building tiny circuits. We're talking Bell states for entanglement, basic basis rotation measurements, or parametrized circuits for small VQE or QoA examples. A massive part of this is mastering core patterns like compute, use, uncompute. Since quantum operations are mostly reversible, if you leave temporary work registers entangled with your output, that garbage entanglement literally destroys the quantum interference you need for your algorithm to work. You've got to compute the value, use it, and then uncompute it.
Moving on to Section 2, the 6-stage learner workflow. Basically, your staged path to the quantum workforce.
This 6-stage progression, it's rigid for a very good reason. You have to start small. Step 1 is building and verifying tiny circuits locally with exact simulation. Step 2, you pick one primary SDK and learn it deeply. In Step 3, you learn how to compile for actual hardware metrics, because your source code means absolutely nothing if it can't map to a physical device. Step 4, you confront real-world errors by running noisy simulations and small hardware examples. Step 5 is studying algorithms and complex resource estimation. And finally, Step 6, you pick your specific domain to specialize in.
Now, picking that SDK in step 2 is super contextual. You don't just pick the best language, you pick the one that matches your target workflow. If your center of gravity is IBM hardware and circuit compilation, you learn Qiskit. If you're doing differentiable quantum machine learning, you learn PennyLane. Need to optimize resources for a fault-tolerant future? Q# is your tool. Looking for multi-provider cloud access? Amazon Bracket. For discrete optimization, you've got D-Wave's Ocean. Working on Google hardware? Circ. Compiling? TCAT. And if you're building heterogeneous high-performance computing integrations, you're looking at QuDQ. The hardware constraint literally dictates your software choice.
Section 3, Education and Community Ecosystem. Let's look at the global pathways and touchpoints.
The cool thing is, the workforce ecosystem is entirely decentralized now. You don't need a specific local degree to break in. You can build academic foundations through location-agnostic programs like Purdue's Quantum Offerings, FIU's Emerging Tech Track, Syracuse Computer Science Pathways, or AIU's Virtual Quantum Computing programs. Or if you prefer targeted industry upskilling, grab professional certificates from MIT XPro and edX. You can even dive into vendor-specific training with D-Wave's Ocean and Cubo workflows, or Google Quantum AI courses using tools like STIM and Crumble. The pathways are there wherever you are.
But hey, learning in isolation just isn't going to cut it. The global quantum workforce relies heavily on community events. Participating in hackathons like QHack, attending the Qiskit Fall Fest, or joining QWorld chapters and workshops are essential touchpoints. And don't forget major industry gatherings like IEEE Quantum Week, Q2B, and the APS March meeting. This is where you practice, network, and officially join the ecosystem as a developer.
All right, Section 4, the Quantum Programming Stack. This is our massive 20-part series recap.
Because quantum programming, it's absolutely not just writing a script. It's an end-to-end engineering stack. It combines mathematical models, specialized languages, and aggressive compilers. You have to navigate strict hardware constraints like qubit connectivity and coherence times, deploy specific algorithm families, and apply rigorous noise handling and mitigation methods. Plus, you have to run statistical validation practices and target distinct industrial applications, all supported by those workforce pathways we just talked about.
Section 5 is all about essential developer habits. We're looking at transferable, classical, and quantum skills.
There is a massive culture shock here for classical developers. In classical software, you assume deterministic execution, right? You can pause the code, print a variable, inspect the state. In quantum realities, direct observation destroys the quantum state mid-computation. You're dealing with statistical budgeting now. The code you write is often vastly different from the post-transpilation circuit that actually runs on the hardware, which means your entire approach to debugging has to be completely rethought.
To survive these realities, you really need to adopt some golden rules. First, separate your problem logic from back-end execution. Always simulate before burning money on expensive hardware. And crucially, inspect your post-transpilation circuits. You need to know what the compiler actually did to your code. Ruthlessly minimize 2-qubit gates and circuit depth. Budget your measurements statistically, and preserve your calibration metadata. Oh, and above all, never, ever claim a quantum advantage unless you've actually proven that classical computers can't do it better. Always compare to classical baselines.
Finally, Section 6, the realistic quantum future. Time to engineer beyond the hype. The absolutely crucial point here is understanding the difference between where we are and where we are going. Right now, we operate in the era of error mitigation. This means we use software tricks and additional measurements to estimate less noisy results on imperfect physical hardware. But the ultimate goal? That's fault tolerance. That uses logical qubits, protected by complex quantum error-correcting codes. It demands massive hardware overhead, often thousands of physical qubits to make just one perfect logical qubit. Fault tolerance is required for large-scale algorithms like Shor's, but it's important to remember that it's not what you're programming on today's cloud platforms.
I really want to leave you with this exact quote derived from our sources because it perfectly summarizes the state of the industry right now. Hybrid quantum classical experimentation is mature enough to engineer seriously, while broad production advantage remains application-specific and must be demonstrated carefully. The tools are highly mature, the SDKs are robust, and the compilers are brilliant. But broad quantum advantage is a specific, rigorous benchmark to be won. It's not just a magical, universal upgrade.
So, here's the big question. As this quantum programming stack matures, where are you going to specialize? Chemistry, optimization, machine learning, cryptography, compiler engineering, or hardware control?